Hello. In this lecture, we're going to introduce path planning, and in particular, we're going to take a closer look at using a grid lattice for representing a navigable space for path planning. So our motivation for path planning is that now that we know a little bit about moving our agent around, we want to be able to support the agent reaching a goal. So we already have the seek behavior, but what if something's in the way? So the scenario that we originally considered when our agent was seeking the target was that it could just form a relative position vector, and then that would be used to define a direction vector, and then with that we could multiply by the agent speed, or the maximum speed or target speed, and then that would allow us to set a velocity and then move towards our target. But that's assuming that there's nothing in the way. And so if there is something in the way, what do? Well, in some cases, you might be able to just slide around the object. So you can think of it as a gradient descent. And you could do this as just part of the characters or the agent's frame-to-frame movement or steering decisions. It could be that if an obstacle is detected, you pick either to the left or the right from the perspective of the agent to go in. We haven't discussed a particular algorithm for that, but there are some strategies for that we'll see in the discussion of steering behaviors. And so that could be effective. You could also, in this case, in this picture here, we have a grid representation of a world. And if you move from one grid spot to the next, in this scenario, with the starting location and the goal that's defined, there's always a cell that you can move to that decreases the distance between the ball and the goal. So provided that scenario exists, it's pretty easy to write an algorithm that picks of the different directions you could go, so like up, down, left, or right, which of those decreases the distance to the goal the most, and then you move to that spot, and then the next opportunity to make a movement decision, you apply the same logic, and you can keep applying that over and over. And as long as there is a cell that the ball can move to that decreases the current from the current distance to the ball, so like the current ball position, that's a known distance to the goal, and then you can pick up, down, left, or right, and as long as that is an improvement on your last position and you pick the best of the four, then you can sometimes get to the target. The problem, though, is that your agent can easily get stuck. So here, depending on how you frame the problem, the ball is either getting stuck in a local minima or maxima. And this could be a problem, whether we come up with a simple algorithm that I just described, moving from tile to tile, or very similarly, if we have continuous movement and we just have a character movement process or steering behavior, perhaps, where we're trying to steer away from an obstacle while at the same time move towards our goal. So we need some way to keep track of path choices that the agent's making and explore possibilities until an acceptable solution is found. And ideally, you would want to explore the possibilities without actually committing to them. So imagine thinking about what you're going to do, what's the best course of action, rather than actually going out in performing everything that you're considering. And so that's planning is what I'm suggesting. So in order to facilitate this sort of process for the path planning, we need a data structure that allows us to represent the different possibilities for moving around in the environment and understanding where obstacles are. And so a graph is a very suitable data structure for this purpose. So we can have a graph that's formed of nodes, and these nodes are connected by edges. And there are many different configurations that we can make of our graph, different information that we can associate with the different components of the graph. So for instance, the nodes we might associate with a 2D position. So each node would have like an X and Y position that's associated with maybe a game world. And then the edges, each of the edges are valid paths that exist. So from one node to the next, maybe we have a line of sight path that we can go from one to the next. The edges can also have additional information associated as well. So this might be the length of the path or the cost of traversing the path, which might involve more than just the length. So you could consider some paths could be more difficult or less difficult, and that might be related to the surface that your agent's walking on, like maybe a slippery surface or uphill or downhill. Another thing is that our edges may have a bidirectional element to them. So there is only a path in one direction, and then you might have an opposing path that may or may not exist, depending on whatever the constraints of movement are in your game. So with this fundamental structure, we can configure in different ways. And you're probably familiar with different types of graphs already from previous computer science classes that you have taken. So we might have a directed acyclic graph that has no loops, directed cyclic graph, undirected graph. You've probably worked with tree structures before, which are themselves a type of graph, a digraph, and so on. And graphs are important in many games, certainly for path planning, as we'll see, but you will often find other examples of graphs as well. For instance, in the board game Risk, the board and the different positions where pieces can be placed on various countries, that is a graph structure. So the relationships and the different actions that you can perform as part of the gameplay are related to the traversal of this graph structure. So the picture on the right, you can see the board. It just looks like a map, but then the places where you can stick the pieces are overlaid with the countries, and then they have certain connectivity that forms the graph you see on the left. You also find graphs occasionally in strategy games that involve building or advancing civilization. In the game Civilization, there's certain things that you can research. So you can have the country that you're leading, you can set as an objective to research certain areas, and then if you do so, opens up opportunities to obtain new technologies or new abilities. And so this sort of concept is pretty common in many games. You can also find graph structure that's just inherent from the way the game itself is built. And this you can see in tile-based games. So many, especially early 2D games, were built with tiles. So each graphic element on the screen is maybe some fixed size, and you can select between different types of tiles and build out a scene. So in this case, we have Legend of Zelda, and there are different tile images. So the level designer and artists work to figure out what's the artwork that goes in each tile, and these also have some gameplay properties like being traversable or not, or perhaps objects that you can pick up. And so this is a case where we already have some graph structure, and the graph maybe isn't immediately obvious, but you can think of each grid as being a node, and then the adjacency with other grid cells define the edges. So we might define a graph for the purpose of path planning that would be all the traversable grid cells. Those would be the nodes that we would consider for finding a path. And then, of course, the adjacency to other traversable cells would define edges. And overall, we would have a graph that we could work with. So you might be wondering about other types of games that have more unique sort of geometry, how we might define a graph. And that's a lot less straightforward than the case of like the Zelda game we just saw. We might have different rooms with pretty complicated structure. And so how could we possibly represent those? So it's possible we could consider each room is assigned a node, and then we connect rooms that are adjacent to other rooms with edges. So this could be a useful approach to creating a grid that would support our path planning. So let's consider a little bit more about this act of planning. So part of intelligence is the ability to plan. And when we're talking about planning, this is the means of considering possibilities that haven't actually occurred yet, and see if there is some course of action that leads to a goal. And so if we can represent the world as a set of states, then we can figure out, well, what can we do to manipulate the current state of the world such that we achieve a goal. So each possibility is a new configuration of the state or states that we're using to represent our world. And then the changes that are applied are called operators. And in the case of path planning, our operators would be the movements taken. So this could be like go north, south, east, or west, perhaps, if we're talking about movement on a grid. But we could also have other operators that we consider for other types of planning. And so this will be something that we will look at in more detail when we get to some other game AI topics. But you might imagine, say, in the case of civilization, you might come up with a plan to research and develop a certain technology that you recognize that you need for success, or your agent. If you have an AI opponent. So let's say that there's an AI playing against you, and the AI recognizes that you have a certain technology that gives you an advantage, then perhaps the agent would identify a goal of a counter technology and then could perform planning on the dependency graph that we saw before in Civilization. So this this notion of planning isn't just for path planning. But in the case of path planning, we have our states, which include the location of our agent or NPC in the space, also our goal location, and then coordinating that information with a discretized representation of the game world or the space. And so this is important because if you think about the typical game world, especially in a continuous movement sort of game, we have a lot of possibilities for different sorts of obstacles and details, and the character can move in arbitrary amounts or placements of the goal or the agent. There's near infinite possibilities there. So we'd like to find some way to simplify the representation in the world, but not so simple that it gives us bad information back if we use it, like apply some sort of algorithm to find a path. We want just the right amount of detail in our discretized representation. But ultimately, this discretized representation, it would be nice if we can map that to a graph structure, because in computer science, graphs are well understood and well suited to the problem of planning. So it's really going to vary how we go about discretizing our game world. It's going to depend on the game and what sort of goals we're trying to support for the agent. So in a game that's already tile based, we already have something that is inherently discrete in the tiles. Even if you have some degree of continuous movement, like in the case of Zelda, the tiles that you get from the layout of the level would be suitable to just work with directly as a discretized representation. You might also have floor locations in 3D or in 2D where you have different waypoints. We could, if a game, for the purpose of the gameplay, we need to consider 3D relative locations. We might use voxels. So think of it as like the equivalent of a grid, but now in 3D, where we have some cube-like structure that we're using. And we could also possibly have what's called a nav mesh, and that is something that we will, a data structure we will learn about in a future lecture. But the basic idea with the nav mesh is to represent different navigable areas with convex polygons that are connected to one another to form a graph structure. Our operators are just a notion of moving from one discrete location to the next. So this allows us to simplify or abstract away a lot of the issues of movement. So it's important that if in the process of discretizing a state, we say that a node is adjacent or connected by an edge to another node, then the agent should be able to easily move from node A to node B across the connecting edge between the two. We don't want that to be something that's like an 80% chance that the agent will be successful. We want to make it a certainty that the agent is able to move. And so there's certain things that we might consider, such that if the agent is located at a node and there's some associated geometry with that node, like a grid cell or a polygon of a nav mesh, If the agent is located, a continuous movement agent is located at any point within that associated area, then it shouldn't matter where they are within it. The agent should be able to easily get to the next adjacent area. So again, the node A and node B of our graph associated with these two areas. So these are the sorts of things that are important to consider. But ultimately, if you create a discretized space effectively and have this well aligned with the capabilities of your agent, then you can facilitate path planning just through analysis of the resulting graph structure. So the basic strategy that we're defining for this process is, well, first we want to create a data structure that facilitates the path planning. And so this is the discretization of the game world if necessary, or leveraging an existing discrete representation like a tile-based game. Next, we need to quantize the agent and goal locations to the graph if they are continuous positions. So the act of quantizing is basically just identifying of our discretized space, or this graph structure, what is the correct node to assign for the agent's current position. Same thing with the goal. Then we want to perform or execute an algorithm that will create a path for us that, if the agent follows, will get to the goal location. So this isn't actually doing the walking around in the environment if your agent is on foot. This is just like the agent thinking about it, and the result is you get back a path that then the agent would need to follow. Now, once you get that path, assuming that there is a valid path, at that point you need to localize the path back to the game world. And so this means leveraging the relationship between your discretized space and the real world. So maybe you have a position associated with each node or some sort of area, and you send that information back. Now, before the agent actually executes on that, you might need to do some cleanup. The path might not look appropriate, or it'll be unnatural in some way, have some sort of artifacts that are a result of the way in which you discretize the space. And so this is where you may need to clean up your path to look more natural. Once you get to the point that you have a path you're ready for the agent to follow, then finally you can initiate some agent movement, especially if this is a continuous movement model for your agent. Then you would start to make moment-to-moment decisions as part of the game update loop, or your agent would. These would be based on the movement algorithms that we've looked at so far, or perhaps some more advanced approach. Now, when we're performing the analysis of our discretized space and the associated graph, and we know where our agent is and where our goal is, so the quantization, at that point, we're going to need some sort of algorithm to facilitate this. And there's lots of different algorithms that we might consider for analyzing our graph and basically exploring all the different possible operators that could be applied to the current state defined by where the agent is and where the goal is and the structure of the game world. And so there are certain aspects to the computation that we're wanting to perform that we should consider. So, for instance, there is the issue of completeness. Will our algorithm find an answer if at least one exists? Then there's the issue of time complexity. So how long will the algorithm take? And usually this is defined as a function of how big our graph is. So like how many nodes there are, for instance. Same with space complexity. We want to know as it relates to the size of our map, how much memory will be required to perform any calculations or storing, caching of data. And then lastly, there's optimality. So as you might imagine, there can be a lot of different ways to get from point A to point B, but we want to find the best one in many cases. So that, yeah, this is the issue of optimality. So we're going to, in a separate lecture, we're going to look more closely at these search algorithms, but I do want to just briefly discuss, just to set up some of the discussion for this lecture. So you could analyze the graph in such a way that you make no assumptions about the structure that led to the graph. So you're not considering any metadata associated. All you would be considering are the nodes and the edges, and perhaps the weights of the edges, but no additional information. So that would be a blind search. Alternatively, you could have a heuristic search, and this is where you are leveraging domain knowledge. So we're going from a general understanding of graphs to something that is more specific in how the graph is being applied. So in the case of path planning, especially in video games, we know a lot about the game world that the graph structure arises from. So for instance, we can perform distance calculations against known positions for each node of the graph. And so this allows us to define heuristic rules. And so these rules we could possibly consider as part of an algorithm. And this could drive low-level decisions as we're going through this planning process, exploring different possible paths. And the end result is that we might be able to improve on some of the metrics related to the performance of our search algorithm. And so, of course, we're going to want the best possible algorithm for our needs. And if you think about what those needs might be for a video game, well, we want to probably have efficient use of memory and processing time because there's a lot of other things going on outside of artificial intelligence. We want the game to be responsive. We want the agents to appear to be able to figure out what they're doing, like where they're going very quickly and not get stalled, as the computer is trying to figure out what it is to do. So it's really an important consideration to try to make any sort of path planning to be as efficient as possible. And that means that we do desire to take advantage of all the information we have access to. And so heuristic searches will probably work best. So we're not going to cover heuristic searches today, but I just want to get you thinking about that. I do want to briefly consider two of the blind searches. So first of all, the depth first search. You've probably, as part of your computer science curriculum, have explored this, especially with searching through trees. So performing a depth first search on a tree is really pretty straightforward. because you can keep track of where you are in the tree pretty easily just based on the nature of a tree structure. You don't have to worry about getting caught in loops, for instance, as your algorithm is going through analysis, and you can leverage recursion. But the basic idea with the depth first search is that whichever node that you consider first, you just expand upon that further and further until you run out of choices, and then work your way back considering other possibilities. So you can apply depth first search to graphs other than trees. And for instance, on a grid, you could consider moving up, down, left, or right. And then whatever the first direction you go, you could just continue to expand that node until you exhaust possibilities. So I've got a little video here from the software that is the foundation for many of the homeworks in the Game AI class. So here is the depth first search, and you can see here the results of that algorithm generating a path. And one thing you'll probably notice is that this path does not look anywhere near optimum. So the two circles that you see where the ball started from, of course, that's the starting position. And then we're going to the goal, and then the pinkish purple line is the path, and you can see the ball following along. So there's lots of backtracking and just in general heading in the wrong direction right from the get-go. So this probably will indicate that depth first search is not really the right algorithm to be using for path planning. Next up of our blind searches is breadth first search. And so this differs from the depth first search in that we are going to consider all of the children of our starting point before we move to the next level, which would be like the grandchildren from our starting point, and so on. This approach can work really well for returning a result, because if you think about it, you're going to be expanding such that you're never going to return a path that is longer than the shortest chain. Now, this can have issues, though, if you have a weighted graph, so meaning edges with different weights, because the sum along any sequence starting from your starting point towards the goal, that can add up differently. So just because you have a short number of edges in the sequence that ultimately lead to the goal doesn't mean that that's the shortest path if edge weights vary. Now, in the case of a grid like we just looked at, all of the distances with four-way connectivity will always be the same, unless for some reason in your game you have modified the weights. So a breadth first search can give you the best result, at least for searching a grid, but not necessarily is that the case with other types of graphs and some that you might see in a game. Like if we considered having waypoints connecting different rooms, like on a previous slide that we were looking at, it's possible that breadth first search could end up returning a result that is not optimal. So here is a video of breadth first search in action on a grid. You can see the resulting path, and this is an optimal answer. Again, this is because we have a grid with square cells, and it's four-way connected. All the distances that are associated with each of the edges in the graph, they're always the equal length. Whether you go north, south, east, or west, you're always adding a constant amount. So that works really well. Next up, I want to look at some examples from actual video games, games involving path planning as part of the gameplay. And we're going to see many scenarios where the path planning fails. So I can tell you that all these games will have some sort of discretized representation that the agents can leverage. And so in this case, we see an agent, I believe an enemy, trying to reach the player. Here's another example. This robot is having trouble with just a small ledge on, maybe hard to see, but there's about a 6-inch ledge relative to the robot there, and it can't get over it, and it's getting stuck. Here's another funny one. There's a panther or similar kind of cat, and it has trouble again with a ledge. So the discretized representation of the world is such that it might not reflect the physical capabilities. So, for instance, the cat may have been able to jump, and this one is really comical. The model here is of a flying creature. It shouldn't even be getting stuck on a ledge, but clearly the game was implemented in a way that is really the geometry of that flying creature was on the ground sliding around. They just had the graphical model floating above. So a common theme of the sort of problems we're seeing is some sort of disconnect. Either the character or the agent, the physical capabilities does not align with the discretized space, or perhaps the discretized space is not complete. So maybe the creature is capable of jumping or easily stepping over, but the plan, they never develop a plan to tell them to do so, so they never attempt it, and therefore do things that seem rather silly. Here's another example. And by the way, if you're interested in watching the rest of that video, I do have links in the lecture notes, so you can check out the entirety if you like. So this is a SimCity example. We can see the path planning performed by the Sims, so the little people that are part of your the citizens of your city. And here, the person who made this video, another on YouTube, this person made 2 roadways, one curved such that it's slightly longer. So the one on the left is a nice highway, looks like maybe multiple lanes, but it's slightly longer. And then the road on the right is shorter, but it's a dirt road, and it's more difficult to traverse. And the Sims seem to be completely unaware that they would be much better off taking the multi-lane highway that's a tiny bit longer. So that's the case where the path planning that's being performed is only considering the length, but not any sort of proper weighting. So in this case, you would want to consider more than the length. You might want to say consider, well, what's the maximum speed that you can go, and then convert everything to an amount of time that it would take, or the amount of wear and tear on the car, or whatever other metrics are simulated as part of the game. So the Sims just are not considering that as part of the path planning. Another example, this is from Half-Life 2. We have a Combine soldier and, of course, trying to attack the player, but only coming halfway down the stairs and not going any further. So you can see that the soldier just keeps trying to find another route. So this is a case where there is, for whatever reason, an incomplete discretized representation of the game world. So the search is working correctly, is taking the soldier as close as they can get to the player, but they're not able to complete the path planning. Here's another example I'll show a little bit of. So this is the Hunter Call of the Wild. And they have some interesting examples of some of the critters you're hunting getting stuck. So in this case, the physics engine caused that, maybe it's a buffalo, to get stuck. Here is an example, I believe, of another that is has identified some path to go on, but is unable to complete that effort because going uphill is too difficult. So again, this is the discretized space is representing this hill, but the analysis, the search, is not considering that angle is too steep to make any progress up. And here is another problem related to the water and not being able to go any further. Here is a deer getting stuck. I don't believe you can tell what it's stuck on, but I think you get the idea that there's lots of possible problems that you can run into if you do a poor job of creating the discretized space and coordinating with the simulated space with the environment, but also the AI agent entity. So whatever the physical capabilities are of the agent. So that can lead to the sort of problems that we just saw several examples of. So tile-based games, again, are nice from a path planning perspective because we have this inherent structure already. Immediately, we have a straightforward way of defining our graph structure, and from that be able to immediately leverage that for path planning. So a lot of tile-based games will have discrete movement of agents. You see this especially often in strategy games, either turn-based or some of the early real-time strategy games had this. And even if it looked like you might have continuous movement just from the animations you're observing on the screen, like say in some of the RTS games, you might notice that the characters or the vehicles would maybe animate between one cell to the next, but you couldn't have like a partial position between the two, perhaps. So this creates a nice situation for just keeping track of where you can go or not go. If there's an obstacle occupying a cell, that's just marked as not being traversable, and therefore you don't have edges of your graph that connect from a traversable cell into the untraversable cell. You can also track enemies themselves occupy spaces, agents in general occupy spaces in the grid, and so you can have a dynamic sort of map just depending on when agents are occupying a spot or not. Those spots or those cells become marked as untraversable. So there's different ways that we might represent our world. Of course, the typical 2D tile is common with a square structure, and we could consider different sorts of connectivity, meaning how we define our edges connecting our different nodes of the graph. So you'll often see four-way connectivity, meaning up, down, left, or right. But you can also have eight-way connectivity where you allow diagonal connections. And that's interesting because if you do allow agents or even player-controlled objects to move in the eight-way connectivity, of course, the diagonals are longer than up, down, left, or right. And sometimes that has implications on gameplay and certainly on path planning. If you're trying to determine the shortest path to locations, you would want to measure correctly diagonals versus the up, down, left, right. One potential solution to dealing with the difference in the distance traveled across adjacent edges of our cells would be to switch to a hexagonal board with six-way connectivity, though this introduces problems with just the complexity of implementing a hex board, but also now you have a lot of zigging and zagging, whereas with the squares, it's easier sometimes to, if you have mostly up and down and left and right movement, to have the squares. So there's trade-offs in going with those two different approaches. So if you have a fully discretized gameplay where the agents move in discrete movements from one cell to the next, this is really the simplest possible scenario you can have for path planning. And your artwork often will be perfectly aligned with the structure as well. So it's just a trivial thing to analyze what type of tile you have. So if you say place a tree in one of the tiles, then that you might have like just a list of integers that are associated with the contents of each cell. And you just have a lookup table and you say, oh, well, this is number 17. That's a tree. Therefore, that's untraversable. And there's not really any further consideration that needs to be made. It's really straightforward, and it avoids the complexity that we'll find with other approaches. Now, if you have a continuous space and you want to discretize, the really challenging part is to figure out, well, how are you going to generate your discretized space? What's the most appropriate sort of representation? Then there's issues of validity, which we will define in a bit. The quantization, so going from the continuous space, the game world, into our discretized representation, and then going back out again, from discretized space to the continuous game world space is the localization problem. There's the issue of agent movement relative to the planning and the quantization localization process. And then also the search efficiency, the implications of any choices we make about discretization could have on our search efficiency. So in terms of generation of a continuous space, you're going to need to consider the boundaries and terrain types. So in some cases, you might have, even if it's complicated, a well-defined delineation between what's traversable or not, such as a polygonal structure. Maybe that would define an obstacle, and then you could use that for any sort of geometric test or analysis to say this is definitely traversable in this one area, but not in another. But in other cases, you have a gradient or possibilities that maybe depend on perspective. So, for instance, you might have hills, and Well, in that case, you might even have scenarios where an agent could go downhill, but they are not able to get traction to go uphill, maybe just according to the physics engine configuration. That would not be possible. So you'd want to be able to capture that, hopefully, when you're creating your discretized space, so you don't end up with situations like we saw before with the buffalo that couldn't get up the hill. So those are the challenges that you might face. We're not going to consider all of these just yet. At first, I want to look at using a grid lattice, but for a situation where we don't have the easy scenario of cells like image tiles that just perfectly fill each cell. Instead, we're going to consider this possibility that we have geometry that is arbitrary shape or structure, perhaps complex polygon shapes, and different orientations and scales and so on, relative to our grid lattice cells. So to perform our discretization, it's pretty straightforward to, of course, just define a grid. It's just a 2D array. And so there's two things involved. One is to size our grid lattice according to our world boundary. So that's like maybe the perimeter of our world. And if we assume that's rectangular, we can just take the dimensions, like the X and Y dimensions. And this is assuming that we are aligned with our coordinate system. But if we have that scenario, we could just say take the width of our game world and divide by whatever grid size we've identified. So what's the width of a single grid cell? So we could divide by that, and then take the floor of that value, the resulting value then being an integer. So that is the largest grid that we can fit inside of our game world. And so here, this particular image shows an example where our grid is the cell size is not a perfect multiple of the dimensions. And so you can see that there's a little bit of overhang of the game world. So in this case, our agent is just not able to traverse into that little bit of overhang. As for obstacles, which you can see from the stone material, those shapes, rectangular shapes, and then there's also a star sort of shape. Those polygonal shapes are obstacles that are, we can find where there are intersections of the obstacles with the grid cells. Grid cells that have any amount of intersection get marked as untraversable, and that is denoted with the blue X's. And so some of those are obscured behind the objects, but those that are not shown, anything that's the interior of the obstacle should also be marked as not traversable. So we need some sort of geometric process to make these determinations of intersection. So definitely want to check out the computational geometry lecture where some of the issues are discussed. This scenario is of wanting to determine how to discretize our space. You definitely want to consider using integer representation to avoid some of the sorts of problems that you might run into if you stick with floating point. But here, let's consider some different scenarios we can have if we have a variety of possibilities that we could encounter. So in this case, we're considering polygons that are concave or convex, but aren't degenerate, and do not have holes in them, and have consistent winding and no self-intersections. So in those scenarios, we can come up with a few different conditions that we maybe look for that would define an intersection with a cell. And if we have identified an intersection with one of our grid cells, we can stop there and immediately mark it as untraversable. Otherwise, we would maybe want to go through exhaustively every possible test just to make sure we catch everything. So first of all, we maybe want to confirm that our world boundaries don't go through grid lines. Just if you generate the grid correctly and you have the world boundaries aligned with your coordinate system axes, then that's not really a concern. But if you did have other more complicated boundaries, you might need to go through steps similar to what we're doing with the obstacles here. But one thing we want to do, verify no obstacle point is within a grid cell, or vice versa, where a grid cell point or vertex is inside of the obstacle. And this is for 2D, by the way. So we can see this visualized down to the left. We have the grid cell in black and the obstacles in orange, and then points that fail the test, or rather confirm the untraversable aspect of the test, are marked in red. So we see the triangle and the one of the rectangles both have a corner inside the cell. So if you can imagine iterating through all obstacles and testing all points of all obstacles, we can see that, the triangle's got a point that tested as being inside the grid cell. Same with one of the rectangles. But you'll notice that all the other vertices did not trigger this test for this particular grid cell. However, we might need to consider the reverse, which is of the 4 vertices of the grid cell. We can test those against all polygons, and we'll see that in fact 3 of them test as being inside. And so in either of those cases, that identifies an intersection, and therefore we can mark the cell as untraversable. Now keep in mind of the logic that we're going through, and that this exhaustive iterative process that we probably need to go through of iterating through all grid cells and all polygons. We don't want to make every possible comparison unless none of them test as an intersection. So that in order to minimize the amount of work being done, we want to quit as soon as we find the first intersection. All we need to do is prove that the grid cell is untraversable. As soon as we know it's untraversable, there's no point in doing any further work. We can move on to the next grid cell. Now we can have, rather than partial intersections, we could have, say, a giant polygon where you'd never have any edge intersections. It would be all the points inside. You can also have the reverse, where you have an obstacle so tiny that, again, no edge intersections, but it's still within the cell. Now, you can, of course, have edge intersections as well, but it's probably less expensive to test for the points versus the edges, and then work your way up progressively to more expensive tests. So, so you basically, in order to correctly discretize a world, you're going to need to go through exhaustively making these sorts of comparisons. There are probably opportunities to simplify things. Maybe if you have complex polygons, you could create a convex hole or a bounding box and do a hierarchical test. And that could be done to avoid as expensive a test like iterating through every single edge of a very complicated polygon if cells are clearly well away. And again, you could do that with a convex hole or a bounding box around the more complicated polygon. Now, one thing that in doing this process, so far we just considered marking the entire grid cell as untraversable and being done. But it might be useful to, if you have a game with continuous movement, it might be worth also marking each edge of the cell as being traversable or not. So the cell itself may be occupied or untraversable, but you mark edges as being traversable or not. And this could facilitate some more complicated analysis. Depending on the game, maybe you have small agents that small enough agents could still go into a partially blocked cell. This is an issue of validity, which again, we will define that in a couple slides here. But I just wanted you to keep that in mind as part of the algorithm. That might be something that you would optionally need to do. Now, in terms of performing point containment on a grid cell, you might think to, well, just treat the grid cell as a polygon. And if you already have a robust point containment test for polygons, you could just use that algorithm. However, we have some standardized structure that we can take advantage of. So assuming that we've got axis aligned dimensions of our grid, which it would tend to be the case, meaning that the edges of our grid cell are aligned with the axes of our space, or 2D vector space, then we can just perform range checks for the X and Y dimension when we do our test, which simplifies things. So you could just do, if you want to know if anything is inside, you could just come up with the appropriate less than and greater than testing for a given test point, the X and Y tested against the minimum and maximum X and Y of your grid cell, and that could be used to determine if this point is inside the cell. If you also want to allow for points being on the edges as well, you could do less than or equal and greater than or equal, otherwise the same sort of tests, and that would be effective. Now, if you're using an integer representation, as discussed in the computational geometry lecture, then you could also potentially just subtract 1. So you know that everything is, all positions are integers, so an int vector 2. So an X and Y would be integer values. You could just subtract a single unit from the size of your grid. So either adding 1 to the minimum values or subtracting 1 from the maximum values would define a new grid cell that's just slightly smaller. And that would allow you to continue to use the less than or equal tests, but effectively only checking for the interior. And so I mention that now because there is a reason why you might want to do that, which will become apparent in the next couple slides here. So next I want to consider some the problematic cases. And this is something that might come up if you were actually using a grid lattice discretization for the purpose of path planning in your game. But the game involved continuous movement and was not a tile-based game. So you're not using graphic tiles, but geometry like this. You may have issues with geometry that is perfectly aligned with edges of your grid cells. And so I've got this picture here, which hopefully demonstrates what I'm talking about. So the red line shown is the boundary of the polygon. We see the blue X's, which show the untraversable area. And then I've marked with the kind of a translucent orange around the perimeter of the polygon. This shows where we don't want there to be any X's. However, depending on how we set up our intersection test, that could easily be triggered. So all of those adjacent cells to the polygon, but on the outside, they do share common. One of the edges of the cell overlaps, is coincident with one of the edges of the obstacle polygon. So we would like to avoid that as something that would cause more of the map to be marked as untraversable. And it's not, if you did have this particular game scenario, it wouldn't be unreasonable that your level designers might want to have some geometry perfectly aligned with the edges of the grid cell, just because it might allow for some more realistic sort of movement, such as your AI agents could walk really close to walls, for instance, which could look better than if they're always offset by some large amount. So this is something I think is reasonably plausible. So we could test only for certain types of intersection. I've got a visual demonstration here showing the distinction between proper and improper line segment intersection. So a proper line intersection from a computational geometry standpoint is one where you have two lines that are not parallel to one another, that intersect somewhere other than an endpoint. And so that would be your ideal sort of line intersection that you might expect. But improper intersections either involve endpoints, one against an interior part of another edge, one endpoint on an interior of other edge, or two endpoints aligning, or perhaps just two parallel lines that have some amount of overlap, including a single point, which I don't have that example shown. But any of those would be improper. And so this would be a way that we could avoid, if we used a test only for proper intersection, we could avoid this. But if we did so, that would create a scenario where if we were iterating through each edge of a polygon and then testing that against each grid cell, what if we had a polygon that was exactly the same size as a grid cell? In that case, you would fail to mark the interior of the overlapping grid cell as being untraversable. So an easy fix here is to go back to what I referred to previously, when the point test for the interior of a grid cell, just using the range check, this notion of shrinking by one. And so this is something that is easy to perform when we are using an integer representation. Again, we can just do this shrinking by 1 unit. And once you've done that, this now means that we will get, when we do the point test against the polygon, we will catch one or all four, in this case, all four of the vertices of the cell would, the shrunk cell would be inside. And so this would still allow us to effectively catch that it should be untraversable. That I think addresses most of the issues to consider in 2D. So next up, I want to discuss validity. And so I mentioned before that as you're identifying each grid cell as being traversable or not, you may also wish to identify individual edges. And so validity has to do with the guarantee that an agent can move from one graph node to the next, or whatever navigable area is associated with a graph node, that the agent can safely navigate from one node to the next adjacent node. And so this picture from the Millington book demonstrates this. So you can see these 2 point positions, and they're in adjacent cells. In this case, none of the grid cells are marked as traversable or untraversable here. We're just considering obstacles that might intrude upon the space of each cell. So on the left, this is considered cells that are partially blocked, but the blocking is valid, at least from the context of considering traversing from one of the partial cells to the other partial cell. And you'll notice that the way that the partial blockage occurs leaves two convex polygon shapes. So what was a grid cell is now a different polygon shape, but it's still convex. However, on the right, you'll see that the way that the intersection with an obstacle occurs leaves the two adjacent grid cells, or one of the two rather, is concave. The other is convex, but one is concave. And so, if you consider convex geometry, any convex shape, you can go from any point along the perimeter to any other point on the perimeter, or from any interior point to any edge of the convex polygon. So any interior point, you can see the entirety of the area of the polygon and the perimeter. But a concave polygon, that is not guaranteed. So when you're thinking in the context of agent movement and being able to safely move from one to the other, the safest thing to consider is just if straight line movement is possible, because then we can use a very simple algorithm like the seek movement algorithm previously presented. So if we have two adjacent convex shapes, then that are two convex areas, that's easy to support. So we can consider, certainly two adjacent convex shapes, like for our grid, that we can easily define those as valid. You could potentially define validity directionally. So even in a case where you do have a concave grid cell, let's say, you might be able to move not up and down, but left and right. So I don't know if you can see my mouse cursor captured well in this video, but like this cell here, we do have a concave shape to it, but the agent could be anywhere in that cell and travel to the left. But up and down, that's not a guarantee. You can easily find positions if you were considering moving up and down that would be blocked or cause trouble. So validity is something you might consider when it comes to creating a discretized space, because it allows you to use more of the map. Now, one sort of practical concern to consider with any sort of discretized space really is, but including a grid cell, is what to do if your agent is outside of the outside of the navigable space, or outside of a navigable cell, and they're not supposed to be. So what do you do? And so this is a fairly common sort of problem. Like, for even with your best efforts, somehow the enemy gets where they're not supposed to be. Maybe there is, maybe the agent got bumped into in some weird way. The collision detection failed. Maybe there is an explosion from an attack, and it knocked the enemy where they shouldn't be. So what do you do in those cases? Well, this is really going to depend on your game, but one thing you might consider is to switch strategies. Recognize that your agent is not on a cell. Perhaps they can just perform local character movement with, like, seeking, for instance. Maybe using raycast to identify if there's obstacles in the way, or some sort of straight line movement. Maybe you temporarily turn off collision detection for the enemy until they get back onto the nearest cell. You could perhaps benefit from keeping track of validity data. So even if a cell is marked as being untraversable, you could at least know, well, which edges lead to traversable cells. You could have agents just move around randomly in hopes that they eventually get into position. Or you could do probably what's one of the most common approaches, is to just cheat and teleport the enemy to be back on the board, or just recognize they're off grid, and if they're not an important agent, like just some anonymous enemy, just have them immediately destroyed. If it's an important NPC, like maybe an escort mission where you don't want the agent to just be disappearing, then the teleporting would work well. And you can use tricks like wait until the player's not looking and then teleport them, or send them off map and then have them walk back onto the map. Next up, I want to just briefly consider how you deal with the resulting path. And so when we looked at the basics of character movement, there was some discussion of how we might have an agent follow multiple waypoints. And so that's the sort of strategy you could use to have your agent follow a path. You just take the path and convert it back to your game world and use those coordinates as waypoints, and then your agent will follow along. The issue, though, is that you will often have a path to follow that looks very artificial. So it's very blocky looking movement, especially it would be the case with a grid lattice. But similar sorts of issues exist with really all types of discretized space representations. And so this is where the idea of post-process cleanup, often referred to as string pulling, comes from. So there's different algorithms, and it will it'll depend on what your discretized space is. So for instance, there might be a particular algorithm that works well for a grid lattice, and then maybe one that works well for a nav mesh, for instance. So let's consider what would be an ideal path or for this scenario shown here in this figure. So we've got an agent that's shown with the gold colored oval, and we have a pot of gold, which is the goal or the objective, what the agent is trying to seek. So the pathfinding algorithm will find a path identified in the figure there, and you'll notice that the starting point is actually not exactly where the agent is. So we have to quantize the agent position, basically figure out what cell the agent's currently in. This is assuming continuous movement for the agent. Then we've got the pot of gold, similar situation. It's not located exactly in the center of the cell. So we have to remember that bit of information to then attach that those little tails to the resulting path that the path search returns. And so you can see that we have go down 2 and then over to the right 3, and that will get to the correct cell. Again, we need to detach those little tails to get to the true locations for the starting point for the agent and the pot of gold. And that's clearly a very awkward path. So this is this induced by the quantization is this backtracking that you see here. So having to go in the wrong direction before heading along the path. And then the path that we see is very blocky. So the idea of string pulling is that you can imagine that there's a string that's located at the agent and at the goal, and then lay the string down over top of the map. Keep the string held at each of those points, but tighten the string. So you keep pulling the string and pulling the string, and it should get tight against the obstacles. And so that resulting tightened string is going to be a much better path, because the string pulling is going to identify inflection points, and those inflection points are the ideal positions to turn. Now, this doesn't take into consideration the physical properties of the agent movement. If there's a complex physics-based model, the agent at their ideal speed might not be able to make certain turns, or maybe would be able to go faster if they, say, rounded the corner more rather than turning right at the inflection point. Now, in the case of the grid lattice, we could consider each cell as being an obstacle or not, and so the orange line sort of depicts that possibility. The actual curve here is doesn't look quite right, because I was limited by the PowerPoint capabilities for drawing the lines. But I think you get the idea, where the bottom left corner of one of the cells marked as untraversable is an inflection point. However, in the actual game world, you'll notice that the big boulder only is blocking just a small portion of the cell that's marked untraversable, so shown with the red. So the yellow line depicts what you may be able to even further improve the quality of the path for the continuous space by maybe testing against the actual game objects that are present. So maybe you could perform tests again by maybe ray casting or some other means against more complicated geometry. Of course, that could increase the computational cost to do so, to perform the string pulling. Another approach you can take is, rather than do this post-processing all in one fell swoop to do the string pulling, you could instead have a steering behavior. This is basically a more complicated character movement, where there's an analysis done of the path, looking ahead greedily to see what's the furthest along the path that can be seen straight line, in a straight line distance. And rather than following the path religiously, instead just use this greedy approach to cut off the corners. And so that will often give results that are similar to the string pulling. So we have some different possibilities that we could consider here. Here's some other examples of string pulling. A couple from the Millington book shown here. So we have the original path as returned from the path planning aligned with the discretized space. And then we have the smooth path using some particular algorithm, and then in comparison to maybe what would be the ideal path. And there's considerations to take, such as the size of the agent. So maybe the agent takes up a certain amount of space, and you don't want to have the agent run into the corner at the inflection point. So the inflection point near an obstacle. So you need to consider some sort of offset to impose. We'll look at those details more in another lecture. I have in the same slide here another picture. This is from an actual game. Now this, rather than using a uniform grid lattice, this is from Star Trek Armada, where they used a quad tree. So it's more like a hierarchical grid, but they faced the challenge of needing to perform string pulling for the movements of spaceships on their 2D maps. So the gameplay was kind of this overhead view. And so they demonstrate how to do string pulling in a quad tree. So it's kind of a unique situation that they faced dealing with the quad tree with string. Next up, I want to consider the search efficiency with a grid lattice. So with the grid lattice, the search algorithm that you use is going to need to visit a lot of nodes. And that's because the search space grows very quickly with a grid lattice. So this is especially the case if you pick a higher resolution grid or a bigger space. So for instance, if you have an n-by-n grid, and this will again be a function of both your cell size and your overall world size that you're trying to discretize. So with an n-by-n grid, you have n squared nodes. And you will also have quite a lot of edges as well. So if you have four-way connectivity, you're going to have n minus 1 times n, then two different dimensions for x and y direction, and then bidirectional connectivity. And then if you're also adding the extra 8-way edges, those extra edges will be n minus 1 times n minus 1. Then you've got two different angles that you can go, like up to the left or up to the right, and then times 2 bidirectional. So you have to add those to the 4-way edge count for the total amount of edges. Now that said, your grid, whatever grid you end up with, you don't actually have to create all these nodes and edges. Your grid itself is sufficient. You can write query methods that just analyze the grid and just on demand interpret to figure out where nodes and edges and paths that you might take. So the operators that are acting on the state information, you don't have to actually like allocate additional memory for that. But because your grid lattice can end up so dense, they're especially a poor match for cases where you have a sparse environment. So you can imagine if you have large open areas and you're wanting to perform path planning, all large areas that you might be discretizing will be filled or represented with potentially lots and lots of cells. So there's really no benefit to your path planning to have all those cells. Ideally, you would want to represent large open areas with as little graph representation as possible. So in summary of our look at the grid lattice structure, one thing that's nice about them is they're easy to implement, especially so if we have an inherently tile-based game with discrete movement. In those cases, with both tile-based level assets and discrete movement, it really simplifies things. Also, if you have that situation, it works nicely with temporary or dynamic obstacles. So when you have other units that are moving in the world, it's easy to, with very simple logic, make a Boolean determination of whether the cell is occupied or not, and therefore whether it is traversable or not. This is good for multiple unit movement. So if you have a real-time strategy game, for instance, this is something that can help to the complexity of group movement is more manageable in this case. And as we discussed already, the fact that our grid structure is sufficient to analyze on the fly to make determinations of where nodes and edges are, or what they are, as we're performing our operations as part of our path planning. The downsides, though, to the grid lattice, it's not great for continuous environments, especially because of not being able to represent arbitrary areas. So you end up perhaps having too many cells representing a large expanse, and especially in comparison to other approaches that might be able to scale the size of the graph appropriately with your game world. And so this is a burden on search efficiency to have all this extra resolution that you may not need as part of your game. And lastly, the path quality can be poor. So the resultant path that is returned will likely need some sort of string pulling to make it look better, unless you have discrete movement in your game anyway, and then it's not as not really a concern at that point. But if you do have continuous movement, you will probably have to spend some effort to clean up the resultant paths. So that concludes our look, our introduction to path planning, but also our look at the grid lattice as a means of creating a discretized space. Hello. In this lecture, we're going to explore different search algorithms that we can use for path planning in our games. So we have previously talked a little brief introduction to path planning, just to really set up the notion of creating a discretized space. And that is allowing us to define a graph structure with nodes and edges on which we'll perform our search. So in this lecture, we're going to talk more about the searching. All right, so just a little bit of review here. So we have previously looked at how path planning is part of formal planning in the sense that we have defined a state for our problem, and then we can apply operators to our state, meaning the current condition of, say, in the case of path planning, the current condition of the agent being at location A and the goal being at location B. So we can manipulate our state representation, which is our discretized space, and ultimately a graph. We can manipulate that through operators that move through the graph, not actually doing the movement in the simulation and in the game world, but just performing the planning. And that if that's successful, you end up with a path that your agent can follow. So what we are wanting is an algorithm that will make the appropriate selection of operators, which basically what are the different routes or small pieces of the route that the agent should take. All right, so we're representing our world with our discretized space. So far, we've learned about the grid lattice. When we briefly mentioned other possibilities like defining waypoints with edges. So the grid lattices has a structure, and the waypoints is an unstructured graph with edges potentially varying length. And then of course, there's other possibilities we've mentioned as well. But the operators generally are always the same. It's wherever you have a graph node, you can follow that edge, or from a node, follow whatever edges it has to go to other nodes and hopefully end up at the right point. And there's two main techniques that we could apply. So one is the blind or uninformed search. This is where you have no domain knowledge. You just you have a graph that fits some defined structure of nodes and edges that connect the nodes. So all you know is what's the start node and what's the goal. You know nothing about the relationship between the nodes and edges until you start to parse through the graph. Now, in the case of a heuristic or an informed search, we do have this domain knowledge. This is typically information that draws from the problem that the graph structure is applied to. So the fact that we have discretized from a 2D vector space, so like a Euclidean space, that provides for us the opportunity to leverage that some information, and will help us to have more efficient searches, as we will see. So in terms of our look at path planning, this is going to be a bit constrained compared to maybe a more general AI study. We're going to focus more on what's most applicable to video games. And so that means that we're going to be interested in these virtual worlds that are static and of finite size. Now, the video games can break both of these requirements, but this is a good place to start. So, and certainly we could have worlds that are not static, but there's usually elements of most games that it's a large static world with just a few moving objects, maybe like doors and drawbridges. But you tend not to see like drastically changing worlds, though there's certainly exceptions. And then also in regards to the size, it tends to be as the world's only as big as the artist design it, but based on current trends, we've seen procedural content generation that could effectively be infinite. It might not actually be, but in terms of the impact on our path search algorithms, that would be the case potentially. But we're not going to consider those cases. We're gonna think that we're going to have static world with a finite size, and also that our operators that we're performing as part of this formalized planning, they're all just agent movements and not anything that like changes state, for instance. So that means we're not considering like pressure plates to open passageways in a castle, or needing to pick up keys or a push blocks around to make a staircase, anything like that. Some of those sorts of things are possible and can be addressed in planning systems for games. But again, we're going to focus on the static. All right, so we're going to stop here, but then in the next video, we are going to take a look at breadth first search to get started in our look at algorithms. Okay, the first path planning algorithm that we're going to look at is the breadth first search. So let's over to the slides. And so I'm sure familiar with the breadth first search from introductory computer science classes, especially related to parsing a tree. And you may recall that this involves starting from the root node, expanding all of the children nodes, looking for the goal or whatever node you're trying to find. And then if that's not found at that level, expand all of the grandchildren and keep going deeper and deeper. And of course, this involves a longer and longer list of descendants to maintain for processing and executing the search. So the breadth first search, in that perspective of the tree search, it works well, and it can find a optimal result if all the edges are unweighted, or at least the same weight. The downside is that you have to maintain all of the descendants as the algorithm progresses to a deeper and deeper level. And it's really, as applied to a graph, like a map, a discretized space, perhaps from a video game, there's similar sorts of issues that you will encounter. So you still have that same sort of maintaining a list of descendants and it getting bigger and bigger the further you spread out from the starting point. So I've got a demonstration here. This is from the software that is used in the Game AI course that's written in C# and using the Unity game engine. So this is running through in incremental updates of the breadth first search algorithm so that it allows to see this visualization. And you can see how all of the nodes, except the ones that are disconnected in the bottom right, all the nodes end up being explored in this case. And you can kind of get a feel for the breadth nature of the expansion. So there's like a leading edge of the expansion that's expanding out in all directions, but it's impeded by the boundaries of the level and the obstacle. So it's maybe not quite as obvious. So let me show you another video from the same software. So this, we can see, spreads out more before it runs into obstacles. So it's almost entirely unblocked. But you can see how it's like if you took a can of paint and just poured it down at your feet and let it spread out in all directions, and then waited until the paint touched the goal. And then you would need to follow how the paint spread to the goal, and that would define your path. And so that's sort of at a high level what the algorithm is doing. So you're starting at the first node and then looking at all the adjacencies to other nodes, and then adding those to a list of descendants, of course, going through the check if it's the goal, and if not, then for all of those descendants, then checking, well, what is the next level of descendants, and adding those to the list. So it's very much similar to the tree search. So it's very easy to implement. It does require some bookkeeping or metadata to track graph nodes that we've already visited. And so we want to do that to avoid an infinite loop, for instance. And we need a queue structure. This is similar to your typical tree implementation. So first in, first out sort of data structure. And so we can actually put our descendants in this list and then keep processing the list for expansion, and then get the right order of expansion for the purpose of expanding like one level of descendants and then the next. We also need some way to track the node, how a node was reached. So as you can think of as like as the paint is expanding, where did it come from? So as the algorithm is selecting nodes to expand, then when a node is expanded, you say, well, it came from this particular node. So you have this from node data. And with that, you can use it to rebuild the path. Once the goal is found at some particular location, you can work back from there. So we need to track open and closed nodes. So there's this notion of set membership. So there's the nodes that we have visited, but they need further analysis potentially. And then there's nodes that we've visited and we're completely done with them. We're not going to do anything with them again other than perhaps use the data for building the path if a given node is on the path ultimately. So we call the first tier of membership, we call this the open set, or potentially the frontier. And then there's also the closed set or the explored nodes. So next up, there's this issue of how do we associate this extra data, this metadata or node records, how do we associate that with our graph? So we could just build it into our graph. So every single node of our map already has some structural elements to denote whether it's open or closed, like maybe a Boolean. We could also have the from node for the backtracking to set the path. But that means that at the start of our algorithm, we have to have all this memory allocated. Also, there might be software engineering issues of cramming a whole lot into these data structures. We might want to keep things independent from our map, perhaps. And so there's different approaches you could take. We could have everything allocated but decoupled and then just have an analogous indexed table, a node array. And so as the algorithm is running, it knows what node is being accessed based on, say, what index does it have in the array of nodes. And then we could have a mirror image, at least in terms of dimensions, another array that's the special node records that includes our metadata. And so the indexes would be equivalent. So you use, say, index 5 for the 5th node to normally accessing parts of the graph. Then we use that same index 5 to grab its node record. But again, this requires all of the data to be allocated. And that actually we might want to avoid because potentially we could find the goal with our breadth first search before some nodes are ever reached. So if you imagine our idea of the paint spreading out and then hitting the goal. Well, there might be further nodes outside that radius that never get explored, and that's memory that would not need to be allocated. So why bother allocating node records for all nodes? And this is a big issue in general for path planning algorithms. So little toy examples, you can certainly get away with it. Maybe even for video games where you have very constrained sorts of maps, it can actually be of benefit to pre-allocate everything to avoid the cost of dynamic memory management. But larger examples, you may benefit from not having the node record approach. Instead, you might want to work with the smallest amount of data possible and minimizing the memory footprint. And in that case, maybe you would use a hash table in some fashion. We could create relationships with the dictionary concept key value pair with the hash of the keys to store our values, the node records, which include all the metadata. We could also just use a hash table for set membership, like the open and close set. We could just add them to this set and then maybe remove them, and also check for membership, like a contains sort of check. We may even make data structures that are a blend of different features. So for instance, you might want set operations and then combine that with, say, a queue, so that you could not only enqueue and dequeue, but also check for membership. A queue in its purest form would not have that ability to check the contents. So these are sorts of issues that you have to consider for practical implementations. All right, so this, at a high level, is the breadth-first search algorithm for graph form. So you want to start by initializing a queue and a set that, or perhaps combined, that represents the open nodes. And so these are the nodes that are under consideration as the algorithm is doing its work. So we're going to prime the algorithm with putting the starting node, the starting point. That would be probably like where the agent is in the discretized space. So quantize the agent's position down to the discretized space, the graph form, and then put that in as the single node in the open queue and set. Then we're going to start a loop, and we're going to keep running until that open queue is empty. So we're going to pull out the current node. And at the very beginning, there's only that starting point. So we're going to pull that out. We're going to look at it and then analyze its edges. Check each edge to see if it's the goal. If it is, then we're going to break, and then we will know everything we need to form the path. Otherwise, we are going to enqueue, so add to our queue the edge nodes. So wherever the edges lead, so that's going to be an adjacent node. So we're going to add those neighboring nodes to the open set. But we're only doing so if that particular node is not in the closed set and not in the open set. And so this allows us to avoid creating infinite loops, this particular check. And we're going to remove the current node from the open set. We've already dequeued it, and so that might be redundant if we have a combined queue and set. But otherwise, we'll treat them separately. And then we're going to add what was the current node to the closed set. Then we're going to go back to our loop, beginning of our loop, the repeat until open queue empty. And we're going to dequeue again. And so we're going to have a new current node. And we're going to keep repeating this process over and over. So it's a very straightforward algorithm. So you may be wondering, well, where is the path? And so once this algorithm completes, which is either it runs out of open queue or it finds the goal and breaks out of the loop. If that happens, then we need the resulting path. And so the way this works is that, as you recall, the metadata that we're storing in our node records includes a from node. And this would be just the ID for where it came from, or perhaps a pointer. So we're going to start with the goal, look at its from node, then go to that node and check its from node, and keep working in that fashion with a terminating condition of is the node that we are currently on the starting point. And once you get to that point, then you have a complete path, but it's backwards. So we need to run a reverse list operation, and then that is finally the result. So then we can pass that information back to the agent, and then the agent could use some sort of agent movement, like to follow a path, and we can see our game perform the path planning. In terms of performance, our breadth first search is complete. This is in the context of a finite static map or graph that results from our maps, which is typical of a video game. So it'll be complete. It'll find a solution if there is one. It could be optimal, and that is dependent on all the edges having equal weight. So if they're of say different distances, then this would be not optimal. We could potentially pick a fewer edges, but that adds up to a longer path, and then we would terminate before we've explored whether there is something that had a longer total number of edges, but the weights add up less. So, for instance, on a grid lattice with four-way connectivity, all the edge weights are exactly the same, with square cells. If we had anything else like waypoints that are not of any sort of uniform placement, then we could get differing results, or even 8-way connected grid would be a problem because the diagonals are longer than the up, down, left, right directions. The amount of time that our algorithm takes to process is the branching factor, which is the edges that each node has. So in like a grid lattice, it's very structured. So we have the four-way connectivity. So that would be a branching factor of 4. And then the exponents of b to the d, where d is the shallowest depth. And so because our breadth first search is going to find the goal at the most optimal, at least in terms of the edge count, then we know we're not going to search any further than that. So that's why it's b to the d. Space is the same because we need to track all that, the nodes and edges, all of them have to be evaluated. All right, so that is a look at breadth first search. It is sort of a jumping off point for considering other possibilities. So next up, we're going to look at depth first search. Okay, next up we have depth first search as part of our look at path planning algorithms. So like the breadth first search, students are probably also familiar with depth first search, especially as applied to trees. So unlike breadth first search where you're expanding all of one level of descendants and then the next, instead you pick just one descendant and then check to see if it's the goal. If not, then pick a descendant at the next level. So you're just picking one branch of the tree to go down, and you go keep looking for the goal. If you reach a leaf and haven't found the goal, then you backtrack. You go up a descendant, check if there's any additional edges or descendants to check, and just keep trying to go to the bottom of the tree and then backing up to the point where you can try an alternate branch. And just continue this until a goal is found. So it's very similar for the graph, to search a graph in the depth first search manner, easily implemented. We do need to address the possibility of the graph containing cycles, because that means that as you're expanding nodes and edges, you might go right back to where you were before. So similar to breadth first search, we need that bookkeeping metadata so that we know where we've already been. Instead of a queue, though, like we had with breadth first search, we're going to use a stack that's last in, first out, or whatever the node most recently added to the stack will be the first one out. So it's a push pop sort of interaction rather than the enqueue dequeue. One thing I want to say about the implementation that I'll demonstrate, and also the code that is part of the game AI assignment framework, is that this is not following the convention for a depth-first search, in that it doesn't free memory for nodes in dead-end paths. They stay in the working memory of the search. And honestly, I'm not exactly sure how to properly free the memory. We'll see some issues that I've encountered. So one is that if you remove nodes, if you're using the same approach as breadth first search to rebuild your path with the from node in the metadata and then being able to work your way back, you might accidentally remove that. And so in terms of keeping track of what the current path is, I think you would need an alternative way of doing so, perhaps building the path in a forward direction. But then if you ever have to backtrack, well, how do you trim your current path if you're not using the from node? I imagine that is possible. I just haven't come up with it. Part of the reason why is that it's fairly easy to make something that works in a depth first search manner, minus the memory savings, just with a small modification to the breadth first search. And that was really all the effort that I was willing to put into my implementation. There's also, I referred to, you may have already read the Russell and Norvig Artificial Intelligence, a Modern Approach. So I referred to that particular book regarding depth first search, and they mention, of course, the memory savings, but they don't show their implementation. So I've had trouble trying to figure out exactly how that would work, but there do seem to be some implications, though perhaps I am just not thinking about the problem the right way. So in any case, my version doesn't have the memory savings, but the graph depth first search is known for having better memory performance than breadth first search. It's just mine does not. And certainly many other AI problems, depth first search is valuable for that purpose. And it's easy to see, of course, in the tree search version. But yeah, I'm not sure how to implement for the graph version. So as you're building the path, if you're not removing the nodes that you've already as you're expanding in the map, kind of similar to the breadth first search, that metadata as it expands, so your open and set and your closed set, you might imagine that potentially the path that spreads across the map, once parts of it become closed, that might cut off from finding the solution. But as long as you're not limited in the depth that you can search, like how deep in terms of a node count, as long as you don't have a limit like that, you will always be able to find a path if there is one, because there will always be you can always go back to a previous node and try a branch off of it that would lead to the goal. However, if you do have a depth limit, there is a scenario in which you can sort of cut yourself off. So potentially there could be a valid solution within the depth that is assigned, but your algorithm won't reach it because the metadata, like the open and closed set, the frontier, is sort of blocking you off, kind of creating a firewall where the solution is not possible. And I've got a little visualization where I can show that to you in a bit. But as for the algorithm, you can take the algorithm that same as used for the breadth first search and just change it slightly by switching to a stack instead of a queue. So you got the same process of priming your open stack and set. And then you're going to just keep iterating until the open stack is empty. So rather than dequeuing, you're going to pop the current node from the open stack. You're going to look at all its edges. And of course, if any edge is leading to the goal node, then you're going to break and do the path parsing and reversal to return it. But otherwise, for each edge, you're going to push to the open stack the edge nodes that are not in the closed set and not in the open set. Now, this is a point where there's another little variation from breadth first search, in that if you do track the open and closed set in this way, as your path is potentially meandering around the map, it will be excluded from going over nodes previously marked as being in the open set. But that means that you have the spacing, especially like if you look at a grid lattice map, you're going to have the spacing imposed by those open nodes that are sort of a fringe around whatever the path that's forming. So you can't have a super close folding back on itself. There's always going to be this offset. So we could allow that to be rewritten. Now, there's a downside to doing that, in that what was our stack structure that only had the push and pop, we now need to be able to remove from the middle, because that frontier edge or the open set, you're modifying it. So if you're modifying it, you need to go and move nodes that were somewhere in the middle of the stack. You need to bump them up to the top of the stack to do so. But if you do allow for that, if you change data structures to be able to do so, you can then have the tighter the tighter sort of path. Now, if all you're concerned about with depth first search is to find the goal, then that would not be of any concern. But if you're using depth first search for other purposes, like intentionally creating a crazy path, then this might be something you would actually need to address in software. So in this little diagram, I'm showing the scenario where depth first search can run into a problem when you have a depth limit cutoff. And so if you've already committed to, let's say, a meandering path that's really tightly packed, and run out of depth, so like you're counting up to the depth limit, you've hit the limit, and then you start working backwards through the open set of available nodes. So provided that you're not returning any nodes in the closed set, like back to their original state as part of this unwinding, if you're not doing that, then that creates a wall. So you can look at this picture here. I've got a starting point, which is the green circle, a goal, the red circle, and a couple obstacles, these walls that are in black. And then I've got a cutoff limit of 40. You can see the path is the solid black line. And so initially I count out a tightly packed back and forth. So maybe just bad luck. This path ends up such that it doesn't reach the goal. Its first attempt going down the depth of its search runs out of length. So at that point, it starts to have to go back and consider other open nodes that might be available. And at that point, those open nodes, their node count is such that they've already accrued all of the meandering that led up to that point. So this is depicted in red. So I picked the best of the nodes that would be open. So it should start, I guess, the cell right to the right of the X. That would be an open cell. And so if you count down from there and go the most optimal it could possibly go towards the goal, you can see clearly that the total count, it's going to still hit the 40 limit and not have reached the goal. But if right from the start we counted like over to the left from green, exactly as far as we need to go in Manhattan distance, which let's see, 1, 2, 3, 4, 5, 6 over. So yeah, if we'd initially gone 6 over and then down, I think it's 8, and then right 6, then clearly we would have reached our goal well within the 40 cutoff limit. So if you did want to limit your search in the context of a static map, you would probably be better off with not imposing a cutoff limit for the path length, but rather taking a subset of the map. So like if you had a grid lattice, you could just take a subset of the grid, and that would limit the maximum search depth, but still allow the goal to be found if it is present. All right, next up, let's consider the possibility that we remove from the, so let's say we exhaust possibilities for a particular path or part of it. So you might imagine that we could just return back to the pool of nodes that would become available again. And so what you would end up with is potentially revisiting that node over and over again in certain scenarios. And so this is, I'm trying to demonstrate how this could play out. So let's say that we've got, similar to the previous slide, we've got a start position, the green circle, the goal in red. And let's say by bad luck, we chose to go to the left when the goal was clearly to the right. And so we have this long meandering path again, and it fills up the entire grid, and we've run out of room. But so if that all just stayed in the metadata is just preserved, the only open node would be to the right of green, and then we would take it and then find the goal, and it would be fairly efficient. But let's say that instead we began peeling back the tail end of the path. When it's exhausted, we move back, and eventually when we clear the bottom row, we would have alternate path directions. Now this would, at least in this case, would require that instead of relying on the open set, we would need to have some sort of metadata at each node that tracks what edges haven't been tried yet. So if we had that sort of approach instead, we could do it, backtrack, keeping tabs on every node that knows whether it's tried all of its available edges or not, and then maybe right at first, just backing up that last row. There's not too many possibilities, but let's say you get all the way back to the node to the left of the green, And so, see, I guess initially we tried going down. So, but then maybe the next time we would try just going to the left, and think about all the different ways that you could draw a line through the grid until you run the end has nowhere to go. So you could just quickly go to one of the corners and get stuck or kind of get painted into a corner. Some might touch every single of the available grid cells, some won't. And you just think about all those different possibilities. And so it, I think, would clearly be a combinatorial explosion. And this is related to some problems like the rook self-avoiding walk, which involves moving the chess piece of the rook. And how many different ways can it draw out a path on a chessboard without crossing where it is walked before? And as the grid size gets bigger, it explodes exponentially. And so, clearly, if we're going to be implementing a depth-first search, we don't want to be creating a scenario where we're trying all of these different paths over and over. And there's going to be a lot of redundancy too, at least on subsets of the path. Because if you back up enough, you're going to start recreating the same structure over and over. So I think you really would want to mark nodes as once you're done with them, you don't want to ever visit them again for fear of creating these sorts of scenarios. And so that's one of the issues I have with the potential memory savings in a graph that I don't fully understand how you could free up for the graph scenario. So let's see. Well, I guess I will mention one thing. You could potentially remove from the available pool, so that while you get rid of something, but you don't want get rid of a node, but you don't want to use it again. You need maybe an additional way to mark something off. So you still need some way to say that a node is closed. You could delete just the entirety of the graph node, but then the graph would be gone. You could have separately your node records. I think potentially you could delete a node record, but you would still need to track closed set membership. So at minimum, that's going to be a pointer per node. So you can sort of see the issue that we face. If we're going to suggest there's a possibility for memory savings. Right, so here is a visualization of the depth-first search at play in the software. And so you can see the leading edge of the path being formed. It does not spread out in that breadth sort of way. By luck, we didn't search the entire available space, but this path is clearly not optimal. It's got a lot of sort of zigzagging. So it's not really practical if you want an optimal path, but it maybe has some interesting structure. So you might be wondering, well, maybe that could be useful in some way. And so maybe we want our agent to wander while still having an ultimate destination. So we want to ensure that our agent gets to some place, but we want them to intentionally demonstrate some silliness. And so you might be dating myself a bit, but perhaps you've seen the Family Circus cartoon. I'm not even sure if those are still around. The little kid, like whenever he's given a task to do efficiently, like take mail to the mailbox, he goes meandering all over the place. And so like maybe you have some gameplay where you do want that, maybe security guard going to a location, and you want to just kind of visit a lot of the area. You could also maybe be generating a maze, and in fact, depth first search is often used for generating mazes for procedural content generation. So this could be something that is useful. So if we intentionally do want silly paths, we might want to make them a little more random than just having that sort of organized structure of always trying like the up direction first, then right, down, left, and so on. So in this case, this is the same algorithm but modified with a little Boolean toggle to tell it to shuffle the edges. So as edges are being expanded, they're actually all placed in a list, and then randomly edges are selected from that list and then the resulting order that they were pulled out of the list is like a card shuffle. So at each point, at each depth or each iteration of the algorithm, that is applied. In this case, the path is avoiding nodes that are in the open set. So it forces the generated path, even though it's random, there's this wavefront of whatever the prior node was creates with this four-way connectivity. It creates those two open set nodes that are right in the way that are blocking. So the only place that the path can form is sort of away from there. It can sort of eventually turn, but those open nodes are sort of pushing along, generally in a direction, at least for a while. But if we allow open set editing, and again, this requires the modified stack so that we can pull things out of the middle. My implementation, I'm actually using a priority queue just because I had already used it for other algorithms. And so that made it easy for me to just edit the priority to change the order. But so in this case, with the editing of the open set, you can see there's no longer that wave front sort of pushing the path along. It can fold back on itself with equal likelihood of going away from where it was before. And just statistically, that results in a tighter path that's formed. And we could even play around a bit with the fact that we have this kind of emergent waveform, and maybe add a chance of open set revision. So only 50% of the time can the path fold back on itself. And here you see a blend of the two. And of course, you can play with that threshold in the code. It's hard coded in my implementation rather than exposed as like a public setting. But you can go in and play with it if you are interested. And we can also check out 8-way connectivity grid. So that is a setting you can easily change in the code. But one thing interesting is there's a little self-intersection. So the path will fold back on itself. So with 8-way connectivity, since you can pass through the diagonals, that is where it generates this possibility of self-intersection. So if you did want to have 8-way connectivity and avoid that possibility, you'd have to mark it off. And of course, if you were using other types of grids, maybe waypoints, then you might have to do some sort of more complicated geometric test as you're performing the search to avoid that. Again, if that's something that you need in your use of depth first search. All right, in terms of performance, it's complete. We will always have a solution if there is one on a finite map. There is, however, the issue if you impose a maximum search depth. then you might have the problem of being cut off by what you've committed to before. In terms of optimality, of course, it's not optimal, but if you're going to be using depth first search for path planning anyway, that's probably not your intent. In terms of time, it is big O of M, and that being the max node depth for a finite map. That will be your all your nodes and edges will be the M value. And for space, it is the branching factor times the maximum node depth will be the space, and that is if you're able to clean up the nodes that are no longer needed. That again, I don't have in my implementation. So the code that's provided, that implementation is the same as breadth first search in terms of its space utilization. So some other ideas for the random depth first search, which I think is really the main direction you would go for path planning in video games, like as any sort of practical use that you could imagine. So outside of just an academic sort of look at depth first search for comparison performance, I think the only practical use is for really the random depth first search. And if you're doing that, you might want to modify it to get different sorts of emergent characteristics. So one might be that you add bias for certain directions, like maybe more likely to go vertical more than horizontal, for instance. And that would be pretty easy to do just with some random number generation. You might also pick a direction to go, and you just keep going that direction until you hit an obstacle, and then you pick another random direction once you've run out of room. That would be easy to do on like a grid lattice. Let's see, you could try to make your paths even tighter together by not only allowing the open set editing, but when you identify, you this would require analyzing all the edges before committing, but you might play with the order that they are added to your stack. So say you've got you're at a particular node in a four-way connected grid lattice. So you've got these three new directions that you're generating, say like left, right, and up. But say to the left, you happen to have an open set node. Well, you could say that, well, that one's much more likely. So you'd have this distribution that you're generating, and you make a decision. Okay, well, we're going to go there at more likely than selecting any of the other nodes. And so that would tend to make the paths you're generating be like really sticky and pull them connected to one another. You probably don't want to do this all the time though, because you'll end up with something that looks very structured. There'll be a few random elements to it, like the elbows where the paths sort of bend, but it might end up looking overly structured, and so you probably want to play with that likelihood. So depth first search is in many respects kind of a silly thing to consider for path planning, but in the context of video games, there may be some special applications where you can get some useful results, like generating a wandering path that does actually end up going somewhere would be a good example. Generating mazes, and we will probably revisit when we talk about procedural content generation. And there's we've looked at a few different ways that we can control the nature of randomly generated depth first search. Next up, we're going to take a look at Dijkstra's algorithm. It's kind of similar to breadth first search. So in fact, let's go back to thinking about breadth first search. So the nature of breadth first search expansion, it guarantees that the shortest path is going to be found for equally weighted graph edges. But it also seems kind of wasteful to spread out the search equally in all directions. Because clearly the goal is in a certain direction. If there's not a lot of like winding hallways to go around like a maze, then it especially seems wasteful. But let's focus on this first issue of the expansion. So again, that works for equally weighted graph edges, but what about scenarios where the edge weights are not equal? And so I have a little scenario here shown with a simple graph. So there is a path A, F, E. Those two edges between the three nodes each have a weight of 5. But we know that breadth first search is just starting at A, it's going to favor stopping as soon as it finds a goal with the shorter distance. But if we look at the sequence A, B, C, D, E, that's 2, 2, 2, 2 adds up to 8. So really that would be the optimum path. And so this is an example where breadth first search fails. So could we revise the algorithm so that it could handle this sort of a scenario? So let's think about what sort of adaptations we might want to make. So one thing is we could add some extra metadata to our node records as we're expanding and considering different nodes. We have a cost so far. And the way this would work is as nodes are expanded, we're going to update this cost so far. So as we pick a node to expand, well, we know where it came from already because of the from node information, and just the fact that the algorithm is on the current node, considering what to expand. So as this occurs, we can just add the total for the current node. When we initialize the next node, we just add the edge length to that running total. And so each node will have a running total for whatever the shortest path was that led to it. And then as far as the algorithm itself, the breadth first search in this adapted form, instead of expanding everything equally, we want to select whichever has the lowest cost so far. So we're not going to use a stack or a queue, but instead we need something that allows us to efficiently extract this information. One special consideration is if we ever have a situation where an open node is revisited from a different from node, then we would need to check if the alternate route that would be formed in this case would be better or shorter, and therefore update it. Now that is not a concern for this particular algorithm, but if we come up with any other further variants, I want you to keep that in mind that we might need to do that. Another issue that we're facing is that if we had negative weights, well, we could potentially have future edges that we might encounter on an alternate route to the goal. So let's say we find a path to the goal using this approach. We might actually have to expand the entire map if we did have negative edges, because there's always a chance that that the running total, the cost so far, could suddenly drop. So turns out for our case, like for a video game with a Euclidean space that we're creating our discretized space from, and therefore our graph is dependent on. We're not going to have negative distances in your typical case. So if we impose this all positive weights condition, then that means that we can stop as soon as we find the node. You're just expanding the cost so far. So this change that we've made to the breadth first search, this is Dijkstra's algorithm. And so Dijkstra originally intended to evaluate the entire graph from the perspective of one starting point, and then when you populate the entire map, like a finite size map or graph, then you could look at each other node, and it would tell you the cost to get to that point, and you'd also have all the information in the map using the from node backtracking that we've seen before. Between the two, it serves as sort of a map from that one starting point. So you always know the shortest route from the perspective of that point. But we can revise this so that we start the algorithm from the starting point and then stop once we reach the goal. And so that is called the uniform cost search. It's a variant, I guess, of Dijkstra's algorithm, and probably more appropriate for our purposes for path planning. So you can think of it as kind of like a breadth first search for weighted graphs. And we can see it in action here. So it appears pretty much the same as breadth first search in the grid lattice, four-way connected grid lattice example. And once we reach the goal here, we'll see that the path looks the same. And that's what we'd expect because all our edges are equal weight. So we're not really even taking advantage of what Dijkstra's algorithm provides to us. So this would be more important if we had like unstructured layout of waypoints and edges. So we would have varying distances, then Dijkstra's would be critical to finding an optimal path, at least in comparison to breadth first search. Let's look at some other examples. Here is Dijkstra's unblocked, at least for most of its expansion. And again, it looks just like breadth first search. Here we see Dijkstra's blocked. And the fact that it does spread out the way that it does means that it doesn't get stuck in a local minima sort of situation. All right, here is one with 8-way connectivity. Let's see, it's not starting. Let's see if I can make it play here. It wants to be full screen for some reason. So this is with 8-way connectivity. So you notice that it's got kind of an octagon look to it. And that is because of the 8 directions. And looks like there's some little video glitch there. Yeah, sorry for the corruption there, but hopefully you get the idea. All right, next up, I've got some code for Dijkstra's that is a little bit more detailed. This is from Millington's Game AI book. I just wanted you to be able to see this for reference and probably help to clear my portrait off there. It also at the very end, it shows the backtracking and reversal to create the path, but this demonstrates the update of our open and closed sets, and the operations for checking, updating our cost so far, and otherwise it is very similar to the breadth first search. Of course, you can check this out probably a little more legibly in the lecture notes PDF. We can consider Dijkstra's algorithm related to games. So back to this issue of the weighting of our edges and the positive value requirement. That's generally not an issue, but maybe there are some circumstances where it could pose a problem. So if the weights instead of distance were travel time, then you might have problems if there were time travel involved in some fashion. And so there are actually games that do involve time travel. So you'll have to find some alternate way to think about path planning if you're working with time. But that is, of course, a very specialized scenario. You also might have teleporting. So you need to watch out for edge costs that are greater than, that are equal to zero. If you had an edge cost equal to zero, then you could get stuck in a loop and keep going back and forth between the two because that would be favored and you'd never get anywhere. So you need to at least have some sort of cost in place. And I have portals shown here. Of course, it'd be an entirely different scenario if you could create portals in arbitrary places related to Dijkstra's. This is rather assuming that you have fixed portals within the static map. So one problem with Dijkstra's algorithm is that you can potentially end up evaluating unnecessary nodes. So because of that, it can be much worse than breadth first search. And this is a little demonstration of how that might play out. We could have many nodes. Of course, we could make this a much more extreme example, but that have small weights. And so those will be favored for expansion. But then ultimately, they could not be the best path to the goal, but they still have to be explored. And then so here we've got the top path that's got a lot of little short nodes, short edges. But then there's this one really long edge at the end that sort of takes us off the making progress. But alternatively, we could have a different direction that has maybe one edge is very expensive, but actually gets us really close. And so this is a problem with Dijkstra's is that it doesn't work well in this situation. In terms of performance, I'm assuming here uniform cost search version. So it is complete. It is also optimal for our, again, recall that we have the requirement that this is a static map of finite dimension. In terms of time, it is kind of a complicated bounds here, at least the equation shown. It's b, the branching factor, with an exponent of 1 plus the floor of c star divided by epsilon. And this is basically it's related to the possibility you could have all those really little small steps, and therefore it can make it much worse than breadth first search because it ends up taking all these little baby steps. If the step cost is equal, though, it's almost the same as breadth first search. The only difference is the point at which you check for the goal. And it, rather than checking at edge expansion, it checks when pulling from the open pool. And because of that, it's d plus 1 is the exponent. And that's the same, it's got the same space requirements because it's got every node visited has to stay in memory. Yeah, so that finishes our look at Dijkstra's. And so next up, we are going to start considering using additional information about our domain. So that will allow us to maybe guide our searching towards the goal in sort of an intuitive way, again, leveraging what we know about our problem domain. We're next going to be looking at informed or heuristic searches, the first of which is going to be a greedy search. So when we first were looking at the basics of path planning leading into creating our discretized spaces, I mentioned the possibility of a simple greedy search. And so this particular algorithm involves, well, instead of searching equally in all directions like we do in breadth first search or Dijkstra's, what if we expand towards our goal? And now this assumes that there's some sort of structure to our graph. It's not arbitrary in terms of the nodes and the edges and the weights, but rather it's connected to some other structure that we can leverage. And so this is introducing a heuristic. And it's a heuristic in the sense that it's like a strategy, but it's a strategy that isn't guaranteed to work. So, well, if I go back to the simple greedy search here, you see that it heads towards the goal, but there is an obstacle in the way. Now, in this case, it's leveraging the distance from wherever it currently is to the goal, and it just happens that it can sort of slide along the surface of the obstacle to keep making progress. So the heuristic could fail, of course, if the path is blocked and you need to go like all the way around some much more complicated structure, and we'll deal with that in a bit. But a little bit more about how we are able to leverage the heuristic. And it's because we have a graph that's derived from our discretized space, and that's dependent upon our game scene, which is a vector space. And so that means there's some geometric rules in place about linearity, and we can take distances and so on. So we've got this sort of dynamic of going from the quantized space back to the game scene, so the quantization to localization. We can go back and forth in terms of our actual game world and the quantized representation. And that also means that as the search is progressing, we can sort of do the same thing, at least in terms of our heuristic function. We can apply the function to the game scene's vector space. Usually that's done through just like a distance measurement, but we could perhaps consider other information that's processed as well. So we have graph edge weights that are based on actual vector space distances. That's an assumption that we have that each of those quantized locations are directly tied to an actual localized spot in our game scene. And so that's how we actually will populate our graph, is through distance measurements and set each of those weights, or at least generally that's the approach taken. So this allows us to, since the weights are based on those relative vectors, distance vectors, we can compare to other distances as well. So as long as we can localize and then quantize back, if we can go back and forth, then we can generate our heuristic. So one thing we might want to do is at some intermediate point of performing our search, we might say, well, from this node, how far is it from the goal? And that could be our heuristic. So that's where you might use Euclidean distance, so the straight line distance between an intermediate node and goal. Or perhaps we'd use the Manhattan distance. So that is like city block style movements where four-way connected grid lattice would be appropriate to use Manhattan distance instead. Now, in the case of the simple greedy search, this is just a gradient descent, and so it will be likely to get stuck. So the way it works is it expands and then it makes current, whichever node gets closer to the goal than the current node. And if there's more than one, then the one that does the best job. So if one is closer than all the, say, 4 options or 3 options, then it will select that. And of course, to do this, at each node that's considered, we need to be able to perform that distance measurement. So if we know where each node is in world coordinates, and that can be something that's just cached and stored. For each graph node, we know like an X and Y position in the game scene space, and we know where the goal is. We can perform this distance calculation using either Euclidean distance or Manhattan, or we could use other heuristics as well. Now, in the case of the simple greedy search, it gives up if there's no closer node, and this is a fail-safe to keep to avoid the possibility of an infinite loop being started. So, because of this, the way it works, there's no chance of loops forming, so therefore it doesn't need any of the metadata to know if something's like in the closed set, for instance. It just can expand right towards where it's going. Of course, the trade-off here is that it's not complete. It can give optimal solutions for equal weight edges, and if it actually gets there, which is not going to be especially likely here. So the time complexity is a branching factor times the depth of the shortest path to the solution. And the memory is just the depth of the solution, because all we have to store is the path itself. There's no additional information. So one thing we might like to do is improve upon this concept of the simple search, but add in metadata similar to Dijkstra's or breadth first and depth first search. They all kind of have a similar approach. And our greedy best first search would then be able to safely explore a way from straight at the goal when it has to, like when it's exhausted options that it would otherwise want to continue following, it can then start to move away. But in this case, it's not going to be able to correct path information. Since it's not tracking cost so far like Dijkstra, that means if all we're doing is considering the distance to the goal of each candidate node, we're just inherently not going to be able to do as well as Dijkstra. And so here we can see an example of this new greedy best first search that is generating the metadata, allowing pathing around When it runs into a dead end or a local minima, it can path around. But you see that it does create this backtracking and therefore less than optimal paths. But if it's unimpeded, like in this example, it just zooms straight at the solution. So it's very similar to the simple greedy. It does have this extra memory that's created for maintaining that open set. But that's not too bad of a price to pay in order to like allow it to still find the solution. Here we have a blocked version of greedy best first search with four-way connected, and it's using Manhattan distance, which is appropriate with the four-way map. Now there are many solutions that would be equally short, and you potentially could have a more visually appealing solution, even though it'd be the exact same length of going straight down and then to the right, all in this one, those long chunks. It might look better to go diagonally or zigzagging diagonally, even though that would be the same length. So that's one of the side effects of using Manhattan distance. Right, here we have 8-way connected, and then it's using the Euclidean distance. And here you see the side effect of its greedy attempt to go straight at the goal as best it can, and then it runs into the obstacle and has to backtrack around. But otherwise, once it's unimpeded, the path looks pretty good. So greedy best first search is complete for finite graphs. It will be optimal if you have equal edge weights. And in terms of time, it's a branching factor to the exponent d, which is the shallowest depth path to the goal. And it does require, in an ideal implementation, that you're checking for the goal at edge expansion to avoid the +1. I believe my version, which you'll see shared, it's some common implementation shared. Between other implementations, it does not do that. So it really, mine has the +1. The space is the branching factor to D as well, because we're having to track information for all of the visited nodes. I think there might be a way with greedy best first search to perhaps free some nodes, kind of similar to the discussion with the depth first search. I'm not certain about that though, but the implementation that I have just leaves everything allocated once the node records are defined for each node. I'm just keeping them there in my implementation. Now, one thing is that if you have a good heuristic, you can reduce the average observed complexity quite a bit, but there's usually going to be there's like worst case scenarios, and that's of course what Big O is addressing. So that covers our look at algorithms that are strictly greedy. So the next thing we might consider is, well, what if we combined the greedy sort of approach versus the breadth-like expansion of Dijkstra's algorithm. So that's going to be A*, which will be our next look at path search algorithms. So next up, we're going to look at the A* algorithm as part of our look at path planning algorithms. So the A* algorithm combines concepts of Dijkstra's and greedy algorithms together. We're going to be, as we expand our search, we're going to be expanding nodes that work on a combined heuristic. So we're going to have both the costs so far, like Dijkstra's, that we're going to be leveraging, but also a heuristic estimate to goal. And that would be like greedy best first search. So we're simply taking the sum of the two. So for a given node n, we can take the cost so far, and recall that in Dijkstra's that accumulates through the progression of expansion. So you start with a distance of 0, and then we take each of the edge weights, which will tend to be the line of sight distance between each node. So that is added to the heuristic estimate, and then we act on that. So if certain conditions are met in terms of how the A-star algorithm is defined, and in particular the heuristics, as well as the conditions of our graph, then we can have a guarantee of delivering the best possible path and potentially perform well as well in terms of algorithm complexity. So an example heuristic would be Euclidean distance or line of sight distance from a given node to the goal. So here is a demonstration of A-star. In this example, since it's going nearly corner to corner, it perhaps doesn't do the best job of demonstrating how A-star can avoid searching the entire map, but we can still see that it does avoid expanding into some areas and will favor moving towards the goal. It does tend to fan out a bit. That's partially because Manhattan distance is being used on a 4-way grid, and so there are a number of nodes that will have the exact same distance. So we can also look at some other examples, such as this one with a direct line of sight, unimpeded. Looks very much like greedy best first search. Very few nodes expanded in this case, and so that is certainly something that is good to see, especially if you're considering selecting an algorithm to use in like a real-time video game where performance is going to be important. In cases where we're blocked, again, we've got the 4-way connectivity and Manhattan distance, so it does tend to spread out. It's a bit like dragging a selection box in a 2D user interface. But you'll notice that from the starting point, it does not expand other than one level to the left and right. And that's just that's the leading edge of the open set or the frontier. If you look closely at the colors of the nodes, you'll see that that's open set. And so it doesn't waste any time going to the left or up in the search. And because there is an obstacle in the way, it's sort of necessary to spread out. So this looks at fewer nodes than Dijkstra's, for instance, or breadth first search. Now we could consider, even with a 4-way map, we could use other heuristic functions. And so it might be interesting to see, well, what if you used Euclidean distance? And so actually I did that. And here is a demonstration. So in this case, it's got definitely a different pattern of expansion. You'll notice that it's the algorithm spending a lot more time expanding nodes to the left and up, unlike the Manhattan distance. And in fact, it's expanded more nodes. And so the heuristic used, the Euclidean distance, is less accurate estimate. So it tends to underestimate the distance from any given node, especially like on the diagonal, because the only way that the ball can move is Manhattan style distance, so either up, down, or left or right. So those, even if you like the end of the path there, that diagonal is the same as going straight down and then to the right. So so the estimate tends to be off, and that ends up resulting a poorer heuristic will result in degrading towards something that's more like Dijkstra's, that's spreading equally in all areas. So it's important to select the heuristic well. Now, Euclidean distance works a lot better with a grid lattice that has 8-way connectivity, as shown here. So now it looks more like an oval that is directed towards the target, and when the front of expansion encounters the obstacles and gets stuck, it starts to broaden more and more. And then finally it kind of gets past the edge and is able to make a relatively direct shot at the location. So the Euclidean distance aligns really well with 8-way, and that allows even less nodes to be searched. Next up, I want to show you the code for A*. There are some corrections here to the Millington book. So if you happen to have a copy of the Millington book, you'll want to refer to this. Also, for programming assignments related to building the A* search, make sure to reference this as opposed to other sources, because this implementation deals with the possibility of reclaiming nodes from the closed set, which is a possibility that some algorithms, some implementations of A* do not address. So the red boxes are corrections where I think, if I'm recalling correctly, there were some names that were not correct based on edits from the previous version. So all the edits weren't consistent, I think was the main issue. And there may have been one line missing. And then the purple box isn't technically incorrect for the pseudocode shown, but a very likely problem that you would run into is that if you are editing a node in the open set, then you need to move it and move its position relative to other nodes. And in the case of using a priority queue, that means changing its priority. And so the conditional there is only addressing nodes that don't need that done. So it's assuming that if you had a priority queue, it's inspecting the node record itself, but your typical priority queue, the priority is separate from the data internal to the structure. So most likely what you would have is an else condition, and then update the priority in that case. Here is an example of from the Millington book of how nodes might look in the progression of expansion in a human readable form for the metadata, the node records that would be necessary. So you start off with node A, it's the start node. You have a heuristic estimate, like a Euclidean distance to the goal, so like 4.2. Also, cost so far is 0. It has no prior node, which is shown in the connection. And then there's an estimated total cost, and that's the G plus H of N calculation, which would be the cost so far plus the heuristic value. And we can tell what set it belongs to because they're it's annotated with closed, so you can assume that that node is a member of the closed set. So very similar metadata similar to what we've seen before with the other searches. And there's so we're midway through the A* search. So several nodes have been evaluated, and then there's a couple nodes that are unvisited. But you can see how the estimated total cost for each is changing, as well as the cost so far is we have a running total, and we can get the data needed to generate this cost so far running total by the edges that have the weights assigned. So for instance, the edge AB has a weight of 1.3. So in generating the node data for B, we take the cost so far of A plus the 1.3. So node B's cost so far is going to be 1.3. Its heuristic is going to be dependent on the discretized location of B and G, which is the goal node. So that we'll need some means of obtaining the XY position in the game world's vector space, which is probably stored in your graph. And then you can just apply the Euclidean distance function, and that will give you your heuristic. And that can be stored in the estimated total cost as the sum of cost so far plus heuristic. And so that's where the 4.5 comes from. The connection is stored, it says AB, so that you can tell the left side of the connection is where it came from. So there's other ways you could store that. You could just say from node and it would list A, for instance. It's also in the closed set just because you can assume as part of the algorithm's progression that this node has been evaluated and moved to the closed set. And so you can check out some of the other nodes. I encourage you to spend a little more time just looking at this slide and making sure you're comfortable with it. Compare it to the algorithm pseudocode. And then also let's consider what happens in the case of certain types of updates that might occur. And that is the possibility that a closed node may be revisited. And so it's necessary to correctly do A* as you're expanding nodes. So if I go back to the previous slide, we will see that node C is open. And so an open node, of course, is available for consideration as part of the algorithm. And it's it's the next node to be evaluated because its estimated total cost is the lowest. Let's see. No, actually, at this point, it's not the lowest. After E is evaluated, it will then be the lowest cost. So if E gets updated, it will become closed, and then C will then be the lowest estimated total cost, which it would be selected and then evaluated. So that's the point we're at in this slide. So it's the current node. We'll assume C, circled in the bold there. E has already been evaluated and closed, but this is a scenario where, as we're expanding edges of node C, we're going to check out E, even though it's closed, and see that if we went from C to E, it would be a better result. And that's because if you subtract away the 1.7 that came from B, and that's originally what led to E being visited in the first place, that will, and then replace it with the C to E edge instead, we'll see that gives a better cost so far. And if that's the case, then it needs to be updated. But the problem is that if we updated it in its closed state, well, that could have an effect that trickles to multiple nodes in the graph. So rather than determine that it needs to be updated and then try to bubble the change right there as specific code. It just happens that you can instead move it back to the open set, and then it at that point has the option to be selected again if it affects the solution, and that will allow the normal A-star algorithm to do the bubbling of the change for you, and so you don't have to have this extra like secondary helper algorithm to do it. So it's kind of an elegant solution. It's just to flip it back to open, and then it can be reassessed if it needs to, and any bubbling that needs to occur will happen. So that's probably other than that, the algorithm is really what you would expect, just switching to a different criteria for expanding. Now, in terms of the algorithm, it is outside of that special case is pretty straightforward, but it does depend on some critical operations that are occurring. So we've talked before about what's the best way to store the node record metadata, and also the data structures we might need, like a stack or a queue. If you are manipulating things that are in the middle of your list, then you suddenly need to consider other data structures. And so that's the case now that we're optimizing this G plus H. So for the estimated total cost. And so because of that, we have these critical operations of adding to our list or whatever the data structure is that we're going to select. So we're going to be thinking about, well, what's the algorithmic performance of adding to our list, removing from the list, finding the smallest element, which is important for the selecting of all of the open nodes, which one has the best estimate. So that's where the smallest element need comes from. And then also perhaps being able to find a particular node, whether it's to retrieve something, some data like a data mapping like in a dictionary, or just to find out that there's a set membership, a containment. So we need to find a balance between all of these operations if we have a data structure that is performing these actions. So the simplest thing would be a naive solution where we have a linked list. So this would allow us to do things like delete items from the middle if we wanted to, or add items and so on. But finding an element in a list would mean that you might have to search the entire thing. And in the context of our A star, this could be happening every single time, every iteration of our loop. So this would certainly have a compounding effect and lower the performance of A star. So really, we would like to be able to find entries more quickly. We could have a sorted list, but so finding would be efficient, but then the cost to add is going to increase a lot, because every time you add, you're going to have to deal with the sorting. And it turns out that if you look at like the distribution of calls that A star makes, it's going to add a lot with much less often finding the smallest element calls. So because of that, we really want to make it more efficient for the adding and also the removing. And so this is where the priority queue comes from, or a heap implementation. So it's a tree structure, but it's based on an array. And I'm not going to go into the implementation other than just to say that this data structure is generally ideal for use in A star. And it just turns out that it's really easy to get the smallest element because it's the head of the tree. And then when you remove the smallest element or add a new element, it's a big O log n. So it's a good compromise given the needs of A star. There are other possibilities that you could consider. For instance, a bucketed priority queue. In some cases, especially in a game where you have like a fixed sized map, there might be a way that you could tune the size of the buckets. You can think of the buckets as just being unsorted lists. So you could minimize the need to manipulate the ordering of your priority queue just by having a bucket of a handful of items. And so there would be like you can probably find a sweet spot, but there's a lot of work in tuning it to get it just right. So it can have performance benefits, but it's often not worth the trouble. So one thing to consider is, well, what happens if a goal node cannot be reached, like it's blocked off for some reason? So when you run your A star, what's going to happen is you're going to fill your graph with your search, unless it's depth limited. And then at that point, you have to decide what to do. Are you just going to return failure, or perhaps you could look for the whatever the closest node is, and so you could do that by looking through the closed set. When you've exhausted the open set, you look at the closed set, and you look for the node with the lowest heuristic score. You've already calculated and cached all that information. So in the case of A star, that it's kind of low-hanging fruit to go ahead and take advantage of that. And it's also leads to reasonable behavior for an agent, that if the agent can't go where it's supposed to go, like say an enemy chasing the player, you might want the enemy to at least go as close to the player as they can get, and wait. Maybe the player hops down from a perch or opens a door and comes out, and the enemy is there ready to cause some mischief. So we're going to come back to the topic of the heuristic function for A star. So we have seen that there's certainly potential for there to be more than one useful heuristic. And there seem to be some implications there, like when we saw the use of Euclidean distance with a four-way connected grid lattice. And so that was an example of a heuristic that still worked, but it wasn't as good. And so there's other things to consider with this heuristic. So regarding A star, the computational performance of your heuristic is very important. You may have actually noticed this. I didn't mention it in the video, but of course, the Manhattan distance is much less computationally impactful than Euclidean distance. So with the Manhattan distance, we're just adding the x and the y differences, absolute differences together. And then with Euclidean distance, we're taking the square root of square sum. And so that, of course, the square root is on your processor. It takes a lot more cycles to calculate. So that's going to have an impact. And we could actually play around with our heuristic at an extreme. So if we set our heuristic to 0, we actually get Dijkstra's algorithm. So that's kind of interesting. And in fact, if we set our cost so far value to 0, so that each edge, for instance, is treated as if they all are no weight, then what you're going to get is greedy best first search. That would be with a heuristic, though, that is reasonable. So if you had a perfect heuristic, then A star would go straight to the correct node, and it would do so in big O of P, where P is your path, the best path to get there. But if you had such a heuristic, then you wouldn't even need to have A star in the first place. So if there was somehow such a heuristic, you would have just a streamlined analysis of the heuristic that would generate the path, and that would have to be some very specialized case. So otherwise, you're in a scenario where you don't know of any perfect heuristic, so there might maybe a bit of an art in selecting a heuristic, and it's going to be based on observation for your particular scenario. So, like, you might actually consider your own game or that you're developing, perhaps, and the nature of the maps, and that's going to drive what's the best heuristic to implement. Now, if you overestimate on your heuristic, like return too long a path, so what we previously saw where we had too short of a path, but not with too long of a path, and if you do that, you may not return the best path. And so, if we look a little bit at some of the details of A star and some of the analysis that's been done of A star previously, there's this notion of admissible heuristics. And so that, as related to A star, is a heuristic that never overestimates the cost to reach the goal. So as soon as you have a heuristic that's overestimating, then it's going to become inadmissible. And that's just terminology. So the words sound a bit like good and bad. And so it's important to realize that that's not really the case. In fact, we may consider having inadmissible heuristics. So that, again, doesn't mean that it's wrong. And it can, in fact, have good empirical results, especially in certain scenarios. But all that means is you just won't have the best answer. It doesn't mean, or always have the best answer. It just means that you could potentially have a very useful answer, and maybe do so much more quickly if you consider computational costs of calculating the heuristic. So Euclidean distance is a standard admissible heuristic for pathfinding because the pathfinding problem is usually built on Euclidean vector spaces, and therefore it would be impossible to have this problem of the Euclidean distance overestimating, unless you had portals, for instance, so that you could just teleport to some location, and then that would introduce a problem. Manhattan distance can be admissible if you have four-way grid movement. In fact, it would be a better heuristic than using Euclidean, which would tend to be too short. And we already saw a example of that. Now, if you are overestimating, you can actually make A star faster. It will tend to home in on the goal more quickly. And this is probably something that you would arrive on empirically through testing and just understanding what the scenarios are that you're dealing with, like in your game. Now, some interesting stuff from the Game AI textbook. It talks about other sorts of heuristics than ones directly based on the distance between two nodes, like Euclidean distance or Manhattan. Of course, that being admissible. But we may choose to use something else like a cluster heuristic. And so this is interesting in that it breaks the graph up into rooms, and these might be structures that you've identified through the process of creating your discretized space. And in doing so, you can assign nodes to belonging to certain clusters, like rooms. And then you just define your distance heuristic as, well, membership in which cluster, and then what are the distances between the clusters. And this can all be pre-computed. So you're avoiding like even doing the distance calculation in that case. And that is maybe feasible because you have just a handful of clusters, so it's not a huge hit on memory, but you have the benefit of avoiding the square root. And so that potentially could be admissible, but it's not a general guarantee. So for instance, you could have nodes that are on the edges of their respective clusters, but you've measured the distance, your pre-computed cluster distances are based on the middle of those regions. Then, so if the two nodes are on the edges that are closest, the two edges closest to each other, then that distance would be smaller, and therefore the cluster heuristic would be overestimating. And so that would be clearly an example of the cluster heuristic not being admissible. But again, don't assume that means it's bad. So we've got an example that's showing in this figure from the book, we have Euclidean distance used to show, well, if you processed a search from the two ends of the path shown, which is from the top left corner to the bottom right corner, how many nodes would be explored? So we see all of the closed node set and the open node set and unvisited nodes. So in the case of the indoor level, the nature of the walls forces the A-star algorithm to spread out. It becomes more like Dijkstra's algorithm with the spread. And then the outdoor level, we see here, it's got this narrow, very, very narrow bit of data that so clearly is the greedy part of the heuristic is being very effective there. And so if you use a cluster heuristic, you can have much better results. So here is how the cluster heuristic might work. Now in this case, we've got waypoints that are, so if you see like this cluster A, it's got 5 waypoints, and cluster B is similar. But any node in cluster B, if you're asking what's the distance between B and A, you would just use this lookup table. So it would be 13, regardless of whether it's this node or that node or that node versus any of these nodes. It would always select the 13. So there's no variation there, but this is very efficient. There's no calculations that are necessary to apply. So here we have the outdoors, and we have two heuristics compared. This is Euclidean for the left side. Again, this is outdoor area with barely any obstacles, very open area, going from one corner to the other corner. So lots of nodes unexplored, which is desirable. That means less processing was necessary. Then the null heuristic, we see that is where we are not using a heuristic at all. The heuristic is always returning 0, and therefore it's Dijkstra's algorithm. And in this case, every single node is explored. We can then compare different heuristics with a star with the scenario we looked at before with the different rooms. So with the cluster heuristic, we have clusters that are associated with each of the little rectangular room-looking areas. So each of those is a cluster. And you can see that we have much better performance than Euclidean. And so, in fact, Euclidean is just barely better than the null heuristic in this case. So this demonstrates that you often hear when someone describes A star to you, they'll often say, well, you should use Euclidean because it's admissible and it works. But if you start digging into the details, especially in the context of video game type scenarios where you would need path planning, the type of game you have really is going to dictate what is the best heuristic to use. And there's a huge payoff in this case. If you had a room that consisted of lots of connected rooms, well, the cluster heuristic, you just need probably just a handful of rooms in that lookup table like we just looked at. It hardly takes up any space. You're avoiding any runtime calculations with square roots. And it has great performance with rooms. But if you had a big outdoors type area, then Euclidean distance would probably make sense. So you really need to consider what the scenario is, and if performance is important, which it usually is in your typical runtime video game where you're trying to maintain a high frame rate, then yeah, you want to look at the heuristic. So performance of A star, in terms of completeness, it is for finite spaces. It is optimal if the heuristic is admissible, but that's not always not always a big deal. We don't necessarily need optimal. We just need pretty good in your typical video game use case. Time is the effective branching factor, which is influenced by the heuristics. This is a little bit different than the other performance analysis that we've looked at. And I will say that the analysis of A star's performance does get pretty complicated. So I'm kind of keeping things simplified a bit in this discussion. So yes, the effective branching factor, which isn't necessary, it's not necessarily the branching factor of your graph nodes. It's influenced by the heuristic, and there's kind of a complicated analysis that goes in determining like how much the branching factor might be reduced to end up with this effective branching factor, and then the shallowest depth for the goal node is applied as an exponent, and so that is our time estimate, and then space is roughly the same as Dijkstra if step costs equal. And so again, this is kind of simplifying things a bit, but it gives you an idea at least of how A star performs. So in practice, it's the issue of memory is going to be an issue before time is in most cases. So we might still desire to constrain A star in some ways, and certainly the heuristic is going to have a big impact because of the effect on the effective branching factor. So just to conclude, A star is very popular to use in video games. It does use a lot of memory. It also has some other issues, like it doesn't work well with dynamic environments. I don't mention it here, but the issue of the heuristic, if you have environments that vary a lot, you might have heuristics that work well in certain contexts, but less well in others. So there's a bit of an art in like deciding what's the appropriate heuristic. And depending on the game, you may find that you need to investigate variants, such as like iterative deepening A star, or just limit the depth, or look at other possibilities such as hierarchical path planning. And so there are, just saying that A star is always the choice isn't really something that you can safely say. You might actually find that that depending on the game, if you have really big, expansive environments and have particular needs for path planning that you can't get around, that you might have to try some more complicated solutions. But this, I think, our look at the various ways we might go about performing path planning gives us a good starting point. And of course, all of this is also heavily influenced by our discretized representation of the game world. At this point, we've only really closely taken a look at the grid lattice, which it's a bit dense in terms of the number of graph nodes and edges in relationship to the game world space. So we'll take a look. We're going to revisit discretized spaces and see. So now trying to make more efficient use of space in the graph size, knowing limitations of A star. For instance, the impact of memory. We want to allow for A star to be as efficient as possible by not having an overly high number of nodes and edges to consider. So we'll stop there and look out for further discussion on discretized spaces for path planning. Hello. In this lecture, we're going to continue our look at path planning. In particular, we're going to look at a new way to discretize a game world space. So this will be different than the grid lattice, for instance. So this is the path network. So the path network is, again, an alternative to the grid lattice and other similar structures, like maybe a quad tree, where we have this uniform structure defining an area. So instead of having that area-based structure, we're just going to rely on positions in the world and associate those positions with a graph. And so this graph will have the typical nodes that you'd be familiar with in other graphs that we've looked at, and edges. The difference with a grid lattice, though, is the grid lattice has the implicit structure. It's each of the nodes of the grid lattice is just known to be the center or some default offset from the dimensions of the grid as it's overlaid in the world. But in the case of the path network, each individual node has its own position. So for each node, we'll have this additional information we store, like a position vector, so like two floating point values. And then we have edges. And unlike the grid lattice, where all edges have the same weight, or all up and down, left, right edges are same, and diagonals are also the same for that category, we could have arbitrary edge lengths for the path network. So this still provides us with a means of performing path planning. We still have the graph structure, and so with that graph structure, we can again do the path planning. And assuming that all of the edges are unblocked in the graph, so each node position is a space that the agent can actually go to, and then all edges are unblocked, then all the agent needs to do is just follow along the path. So it's really a pretty straightforward means of discretizing the game world space. So why would we consider using a path network over the grid lattice? Well, probably the first thing is that we can consider one of the main deficiencies of the grid lattice, and that is that it is not very space efficient. It uses up a lot of memory with unnecessary structure, even though overall it's an efficient structure with the uniform layout. It still ends up being pretty wasteful and has a big impact on the search efficiency. So those are certainly things that we would like to avoid if possible, and potentially the path network will help us get there. So the path network, we have this ability to sort of be variable in the way that we might put a lot of nodes and edges in one area of the game world, and then maybe a big open area, say like a desert or outdoor area. The nodes and edges could be very sparse. One other thing we might be able to achieve with a path network is the paths that are returned might not have that aliasing sort of effect from the quantization part of the discretized space. So the jagged, zigzagging sort of paths that the agent might need to follow, which is problematic for continuous movement agents, not necessarily a big deal for a game world where we already have discrete movement that is exactly the grid. But so this would be much more appropriate for continuous sort of movement. We do need to embrace this new agent movement paradigm, and that is because the nature of our path network, it has no area to it. We have nodes which are just single positions in the world, and we have edges which are just thin lines. There's no area to them. So the agent really can't be exactly on the path network. It's more going to be in the vicinity of the structures, the nodes and the edges. So in order to make this work, we need to embrace that the agent will have these different types of ways of interacting with the game world. So one we'll call local movement, and the other is remote movement. So local movement is just when the agent is moving around with normal movement, like kinematic movement or steering behaviors. This is based on observing positions in the game world, such as like where an opponent is, other agents, collectibles, and so on. Those are positions that are easily accessible. We will likely include some sort of visibility test. So anything that the agent is doing locally will be based on being able to see the thing, that either the location they want to go to or whatever artifact the agent might want to move towards. So this could be based on a raycast, for instance. We could perform a raycast against multiple objects in the vicinity. And if we don't have an occlusion during that raycast, then it's safe to move towards whatever that is. Now we also have this other mode of movement called remote movement, and that involves the path planning system. So the agent can request a path returned from some separate process that does the path planning and returns the path, and then at that point the agent follows the path. And so this won't involve likely won't involve walking precisely on the line. Certainly the agent is going to have like a radius or some kind of width, so it's going to spill over to the left and right of the line as it heads down it anyways. So we have to be aware that there's this lack of precision here. During the remote movement, the agent can either be on the path, following from node to node, and staying on or very close to the edges. Again, it's unlikely that the agent can be perfect, but we'll still consider that being on the path. And then the agent can go off the path, and this is usually because of some sort of interruption, either a dynamic obstacle has gotten in the way, maybe some opportunistic sort of opportunity or task pops up, like go pick up something like a goodie. There could be an emergency. Maybe the agent has encountered an enemy and has to go fight the enemy. So during this time, the agent can remember where they were before on the path, and then go into a local sort of movement based on kinematic movement or steering behaviors, and then do whatever needs to be done. And then assuming they get to a point where they're finished and want to go back to the path following, they remember that the point where they left. And so they'll attempt to steer towards that just with, again, local movement. Once they get to that spot, then they can safely begin following the path again. So this is a bit different in terms of how we have had agents moving before, where they're always on the navigable space. Now they're not. So that is a new challenge to deal with. And so it's something we have to be aware of. So one design implication because of this is that in order to be able to use the path network, our agent's local movement must be robust. So have to have effective detection of obstacles, reliable movement on terrain of various types. Whatever is part of the game, the agent needs to be able to reliably deal with it. So that potentially makes implementation a lot more challenging. So I want to go through an example, basically highlight the high-level steps of the algorithm. So here I have a game world in 2D with obstacles. You can think of these as like buildings or hallways. And we have our path network, of course. So we have nodes and weights. And so the first step is, let's say our agent wants to perform remote movement. So we'll put the agent into the world. We want to find the closest visible node. So this is a situation where the agent is going to query all of the local nodes. In the worst case, like a naive sort of implementation, we would just check against all nodes of the graph. But in a bigger game where performance is important, we might have some sort of additional spatial subdivision sort of structure, like break up the space of the world into bins of some sort. So this might be like a grid lattice, but only for the purpose of defining neighborhoods of objects. So you can figure out, well, which of the bins the agent is in, and then what are the nodes within that bin, and then you also search the adjacent grid cells in those bins as well. So this is a common sort of data structure that is used in games. But once you have your neighborhood of nodes, you can then perform a ray cast to each to see if casting a ray from the position of the agent towards each node, is it unoccluded? So meaning you don't get any collisions with the ray as you aim towards the node. Now in this case, the example shows one ray cast to the right, and node A is blocked clearly because of the wall. But then a ray cast to the left, shown in green, is able to get to the node G. So the agent is able to see the node. And so that's the first step. Next, we need to do a similar process for our goal. So we have a goal to get to the pot of gold. And so for this pot of gold, we do the ray cast. And now this situation, we have more than one visible node. So we are going to pick the closer of the two. And so had the agent seen more than one node, we would have done the same thing, pick the closest. So now we have a starting node in the path network and a goal node in the path network. We also have these little tails, the little tail to get the agent from where the agent is currently to the start. And then once we get to the last node in the path network, that little bit to get us to the pot of gold. So we'll remember that and append it to whatever the result is once we have a path. So we request the system, the path search system, to perform a search. This would likely be an A* search. And so here is an example result path. And so the agent can now begin the remote movement process. And so this will involve following the path. So first we'll complete that little bit, that little tail, extra bit that gets us to the beginning of the path. And this, from the agent's perspective, it could have already been past all of this information. So it's just one complete path, but it might have to separately steer to the node before it can then follow the path. And then at that point, the agent will follow the path and then finish off the little tail that gets to the pot of gold. So it's really a straightforward process to use the path network. But you may have noticed some issues here. So one is that there's some inefficient movement. So from the perspective of where the agent started from and where it was going, this particular path kind of led it along a less than efficient route. It's definitely a lot smoother than the like four-way connected grid lattice zigzagging along the grid cells. So certainly smoother than that, but we do have this kind of odd veering away from where the agent clearly needs to go for the most efficient path. And then especially bad is the strange double back as a result of the quantization. So when we were determining the closest node to the pot of gold, it actually created a scenario where the agent, when following the path, has to backtrack to get to the gold. So ideally, we'd want the agent to take a more direct route to get it. There's other concerns that we have in this sort of scenario, and that would be when the agent cannot see a node from its current position. And same with a goal. You could have the same sort of scenario with a goal, like the pot of gold. So in this case, where does the agent go? So we might have to consider some solutions. So we may, the agent started in view of path network nodes, it could go through a process that it keeps checking to see if it can still see one. And if not, it drops like an intermediate waypoint. Kind of similar to going from following the path, getting interrupted and going off path. We could extend that process to maybe remember where it left, and then hopefully be able to see that whenever it's done doing, the agent's done doing what it's doing, hopefully it can still see that point. You could get more complicated and chain together multiple intermediate or temporary waypoints as well. And in fact, we'll talk about dynamic waypoints in a bit. We also might be able to come up with something with just the local movement, such as following along the edges of walls. There could be something we do, maybe dividing the edges of the path network into points somewhere along, partway along the edges, to create more nodes. Of course, this could get expensive, but so like subdividing edges and keep creating new virtual nodes, to then the agent could test with the raycast to see if it could see those. And so that would allow the agent to figure out the right way to go to get on the path. Another thing you could do is just teleport the agent. This could work especially well if the player can't see. So if the player's not looking, just teleport the agent, and they won't even know what happened. They'll just know that the NPC is now doing what they're supposed to rather than being stuck. But there's a lot of things that you could try to do here, but I think this really indicates how the agent needs to have more robust local movement in order to take advantage of the path network approach. So you might be wondering, well, how do you go about building a path network? And there's two main strategies. One, you could have a manual placement process, like using a level editor, and then just drop nodes and then connect them to make edges. This can be very tedious, but it can have very good results. And you might have some sort of hybrid where, say, you have manual node placement, but then automatic edge forming. Or it could be totally automatic. And the advantage there would be that it'd be quick, but it tends to be inefficient, especially in terms of how many nodes and edges need to be placed. And it can also be very temperamental. Like if you tune some system that does this automatic placement, and then say you have some new level that your development team has created, and say you're in charge of building the automatic placement of nodes, you try it on the new level, and then it's not working with the new level, even though it worked with prior levels. So it can be kind of a temperamental sort of thing. But we'll look at some automatic methods of placement. So one is that you could have a flood fill. So you start with some seed position, and then you determine offsets in various directions and just iterate through, like to the left and right, up and down, and so on, and start placing nodes. And of course, you don't want to place a node if it's not a valid position. So if it's inside of an obstacle, you would just either delete it or never place it there to begin with. And so the whole growing process, this flood fill, is constantly analyzing the game world to decide whether that is valid or not. And same thing with the edges. The edges can be created, at least a candidate edge can be created and tested with the world to make sure that there is nothing that intersects with the edge or gets too close to the edge. And we would probably have an offset by the agent's collider radius, because we want to ensure that our agent can actually traverse down each of the edges without bumping into anything. A big problem here is that this can be as dense as a grid lattice, but you're losing out on all the uniform structure and memory savings. As you recall, with a grid lattice, you don't actually have to store in memory positions for where the graph nodes are. You can derive it at runtime just by the index into the grid, and then the cell width. You just can multiply that out, and that'll tell you where you are in the world. Same thing with the edges. You don't actually need to store the edges because it's already part of your grid. So you can just analyze from a current cell, like an IJ position in a grid lattice cell. You can say, well, do I have a clear path to the left, the right, up, down? And just by analyzing relative to that IJ position. So none of that needs to be stored for the grid lattice, but with the path network, each of your nodes is going to have a position vector in the game world. But again, with the flood fill, you have this automatic structure. So it's not very useful. You might could add an additional process. Say you first grow out this very dense structure and then go through like plucking away nodes. You might be able to automate that, try to identify how many nodes could be taken away. But that could be a very challenging sort of process to implement. Another more popular approach is to use points of visibility. So this is an automatic technique for path network placement. And we have features in our world, perhaps that maybe geometry of a building, hallways, and so on. And this will create natural inflection points. So you can imagine that these convex angles that are part of the geometry, they get in the agent's way. So the agent has to steer around those features to get where they're going. And the most efficient route is going to be getting as close to those features as possible. So if you think about like pulling a string through an environment and pulling it tight, it's going to get pulled up against those corners and be right at those inflection points. Now, the actual path the agent would have to take, having some radius to the agent, would mean there's going to be some radius to the turn. So there's going to be an offset from the convex corners of the walls or other features. But then as that offset is applied, the most optimum route would actually be a curve. But we can just approximate it as just an offset to a point, and then the agent can turn at that point if, say, they're following a path network route. But the idea is that you identify all these inflection points, and then you can connect the inflection points with edges. So you make path network nodes at the inflection points or at the offset position, and then you connect edges just by line of sight. You could possibly cap how far an edge connection could be made. So like maybe you only make edge connections that are within some number of units away. But this can create a functional path network to explore the full environment and can give pretty good path results. This can be an expensive process to identify. You probably will end up with lots of these points of inflection, or the convex points to perform the offset. So you probably really want to have some sort of simplified version of the geometry. Often you can get this from the physics collider. So visual features like what's drawn on the screen, it's often more intricate than what's used by the physics system that is like approximate geometry. And so that would be a lot better for running this process of generating the path network. So in order to place these offsets, we could find a bisecting line of each of the convex angles, and then just along that line from the corner of the convex corner, just move from that corner point out by the radius of the agent, perhaps plus a little further distance just for fudge factor. And then that would be where we actually create our node. And so we can do this a first pass generating all of our nodes, and then go through just a brute force process of testing with a raycast, or actually a distance from a line segment would better capture what we need, because we want to make sure that the agent can fit along a corridor from each of these points. So that it would include edge intersection, but also the offset would be tested for. But once we do that, that'll create nodes and connected edges, and then we can use that in our game. Here is a visualization of how this process would work. So we start with some geometry that we then get an offset from. So the geometry shown in gray, the offset is in blue. And so that would be these points. Then we just, again, go through this brute force process of checking for what edges that we can connect. And so once all of those edges are connected, and then we can pass that on to our game. Immediately we can use it. You might find that you want to maybe have some sort of hybrid approach where the game developers could maybe add some extra points, maybe combine points of interest, say collectibles, spawn points. Depending on the game type, you might add some additional nodes just to make it easy and not rely so much on local movement for the agent to get to other features. And so the paths you do get will tend to hug walls and go right at the point of inflection for turning. So once you perform your path search, you'll have some pretty good paths with this route. Downside, though, is that you can get some unnecessary nodes and edges created. Again, you might have a fairly complicated environment. This got like architectural features that cause a point of inflection to be recognized, but is really more resolution than you need in terms of the discretized space. So that can be tricky to get right. You might end up wanting to go in and delete things, or adding hints to the game scene that, or mark regions and say, don't create nodes in these regions, and so on. And you can kind of end up going down a rabbit hole of adding these extra features so that you can give hints or have better heuristics for this automatic placement so that it does what you intend. But it ends up possibly taking a lot of work. And at some point you might think, well, maybe instead of trying to force the automatic path network to work, we might instead just use like a nav mesh, something like that. So it's something to consider is what level of complexity are you willing to take on just so that you can get the path network to work. One other thing I want to say about the points of visibility is that you could potentially try to automatically find other points as well. And so one thing you could do is maybe certain concave angles, you could possibly try to place points there, but it's a little bit more challenging to do. And of course, doing so will have no benefit in terms of path quality. And if you already have robust local movement for your agent, this would be pointless because the agent could just go to one of the points of visibility as the goal, and then if they needed to get near something in the corner of the room in one of these concave angle areas, they should be able to do so. But if you don't trust that ability, that would be a reason why you would want to maybe place additional ones. So if you were to place at concave angles, maybe like the corners of a map, you have to, in addition to finding the bisecting line of the angle, you also need to find the offset from the two edges that make that angle. So like the two walls, for instance, you need to offset by at least the agent radius, probably more. So you probably, again, add a little fudge factor, and then determine a point along that bisecting line to place the center of the, or place the path network node. So again, this isn't especially useful. I just wanted to point out what would be necessary to do so. probably a more useful thing would just have these points of interest. Again, that would be associated with like game world features or objects like spawn points and collectibles, that kind of thing. All right, so let's suppose maybe we have a situation where we have candidate nodes already defined. So this could either be part of manual placement, like a hybrid manual placement, or it could be part of a fully automated system. This would just be the second step after having found a candidate node position. Now we want to start evaluating a collection of nodes and determine if we have a valid edge between them. And so by a valid edge, I mean that we have an offset from the line segment such that the agent could fit along that entire length from the starting point to the end point. So we can use the agent's radius as an offset of that line segment. And so that would ensure that if the agent is perfectly following that that edge as part of a path, then the agent can fit. So we can use a couple different tests. So one would be the point distance to a line segment test. And then we can also include a line segment intersection test. So if we have both of those tests, then we can do the necessary evaluation, assuming that we can grab the appropriate information from our game world in terms of lines and edges of obstacles. But ultimately, if the corridor is clear from the starting point to the end point of the edge segment, then we add that to the graph. So we connect the two nodes in question. So here I've got a figure that considers the different possible scenarios that you might run into during this process. So at the top, I've got a valid edge shown in the yellow or gold color. The agent is shown in blue. So I'm going to, hopefully you can see the mouse cursor here. So here is the agent shown as if it was moving along the corridor. And you'll see that we have a starting point for the edge segment and an end point. So those are two candidate nodes. We could define this line segment, and we could check for distances to nearby points, or a naive approach would be to just test against all obstacle points. So that would include, in this case, we've got two obstacles with 4 corners each. So we could test against all of those to if they're closer than the radius to the line. And we also have the boundary corners as well to test against. But another possibility is that the points of the lines that or edges that you encounter might not be within the distance. So then you have to consider the impact of edges. So you would want to test against all 4 sides of the obstacles to perform an intersection test to see if any of them intersect with this candidate edge. And also the 4 sides of the boundary we could use to test. But then another possibility is a parallel edge condition. So like, what if the edge was really close to, say, the boundary? In that case, the vertices of the boundary wouldn't be too close to this candidate edge, but it's rather the other way around. The vertices of our candidate edge are too close to the edge of the boundary. So you got to invert your tests. You have to consider for both perspectives to catch all cases. So you have to do the point distance to line from the perspective of the candidate edge, and also the perspective of the edges of your obstacles and boundary. And then you also will perform the line segment intersection test to see if they actually cross. And so you can see some of those other scenarios here. So we have, there's a candidate node that is outside of the game world. So in that case, we can just screen with a range check and immediately identify that to not proceed further with that one. Over here on the right, this test distance failed. That is a failure. The solid red line shows what the failure was, and that was it was too close to the boundary. So that would be the distance to the boundary line of that node was too close. Here we have an intersection test fail. So this node here, there I've got the mouse near the bottom. It is clear of it's the radius distance away from the lower boundary, which makes potentially good. But at least when we try to connect it to the upper right node, you'll see that we get a line segment intersection against 2 of the 4 edges of the obstacle. Of course, the first time we test against even one edge that fails, we don't want to continue because it's just a waste of processing power. So the first failure we encounter, we probably order these in some sort of hierarchy or priority, so that maybe the more likely to catch a failure are first, or maybe something related to the computational cost. So depending on the way we order this, it could be more or less expensive. Certainly we want to have these short circuit exits or continue on looping with other combinations. Another failure we have here on the bottom, so this path node in the bottom labeled with the text path node, we could cast draw a line segment over to the left, and so that looks like we wouldn't have any edge intersection. So we have a clear edge, but then look at the distance from that edge to the lower corner of the big obstacle, and so you'll see that distance is too close. So that is a problem. So that would be the distance from line segment to point test, and compare that to the radius we see was too small. So we have to abandon that possibility. Over here to the left of the big obstacle, we have this node, and it is too close to the edge of the obstacle. So this is where we consider from the other perspective. And so that would cause this edge from being created. And the reason why that is because if the agent tried to go all the way, say, go to the left and then down following a path, it can't get that close to the obstacle. So it doesn't have a fully clear corridor. So just with those tests, we can, if you're careful in how you set things up, you can capture all of those different possibilities. Next up, I want to look at a bit of a tiny case study. This is from the game Quake. It was highly extendable. id Software made it such that hobbyists could make their own mods to the game. And this one particular person, Steve Polge, made an agent that could play deathmatch. I recall back during the time that this work was done, people that were fans of games used to, if you wanted to be in like a discussion rather than Reddit, you just use Usenet, or the old school news groups. And I remember a lot of debate talking about how no one would ever be able to make a deathmatch bot that could provide any sort of challenge to a human player. And so Stephen took on this challenge and began implementing his own bot. And so this bot actually ended up working really well. In fact, gives a lot of good deathmatch players a hard time. It was never even complete, but was still really impressive. And the reason it was incomplete is because the work he did was so impressive that it drew the interest of Epic Games. And so he was hired and ultimately built the Unreal Tournament bots and worked on a number of other games. But the Reaper bot is interesting because it used path networks for movement. So the picture in the lower right shows one of the Quake editors with path network nodes that are placed. You cannot see the edges. So you could either make handmade packs of nodes or handmade path network for recognizable levels. But then if, say, during a multiplayer deathmatch, there's a new level that was unrecognized, the agent could even dynamically build path network. And so that was something I wanted to consider is well, how might you have your agent perform the building of the path network? So you can think of it as like breadcrumbs, dropping breadcrumbs. So this, of course, would be similar to what Hansel and Gretel attempted. Of course, I guess the birds ate them all, and it didn't work out so well. But in the case of the agents, they can just store things in memory to keep track of where they are. The idea is that the agent drops waypoints at important locations, and from doing so, creates a complete path network. So at a high level, this algorithm would work by you start at some initial location, that would be the first node, and then each think update. And this update could be not as often as the frame rate of your game. It could be slower, perhaps. And the reason you do that is for performance reasons. You won't want to do all these computations every single frame. So you maybe skip a few. So during this update, you check to see if from the current agent position, can they raycast cleanly to the last waypoint or perform the distance to line segment sort of test. Most likely it would only be a raycast, though, because it would be impractical to test against all the obstacles around it. It'd be hard to facilitate only identifying the closest obstacles. So you do this test, and so as long as you can still see the last waypoint, there's nothing to do. But if you can't, then what you need to do is store that last waypoint as a node, and then basically continue on this new path. So every time that the agent can't see where they're trying to remember where that last waypoint is, like it's occluded, so they walked around an obstacle, then that's when you need to start a new waypoint. And so these keep getting dropped, and you constantly are testing. So just continuing on a chain is really pretty straightforward. It's got a constant load in terms of performance, and the memory will depend on how often, like how many nodes you store. It's going to depend on how often the path gets occluded. Eventually, you run into the scenario where you loop back on yourself, though, and so this is where you run into issues, because you would want to reconnect with the previous parts of the path you created, and also be able to leverage those points to avoid just creating nodes on top of nodes on top of nodes. So the agent has to be aware of those. The problem is this building process can get pretty expensive, and the load will vary, and you're trying to maintain a real-time performance of our game, and it's getting worse and worse. So sort of dynamically managing that is going to be a challenge. I believe in the ReaperBot's case, there was a cache of a fixed size. So things fell off the back end of the cache if they weren't used often enough. And so there were some levels where the cache was not big enough, and the agent could get caught going in circles because it would forget what it had learned before it came back again. So it didn't always work perfectly, but it does have some potential. So applications of this sort of dynamic path network approach, it could be great in scenarios where maybe you have procedurally generated worlds. So there's no way that you could pre-author or bake the path planning into the game. You, like, as the player explores these new parts of the world, if you did need to have agents be able to perform path planning, maybe like pets, some kind of sidekick, or maybe it's just a much more complicated procedural content generation sort of game where you do want to have some persistent agents, then this might be critical to getting it to work. It's something like this where you could dynamically build the path network for the agent. And this could also work in scenarios like the ReaperBot, where the developer just couldn't take on the effort to hand make path networks for every single deathmatch level that was out there. So if someone was running the bot, it would be nice if the bot could just work on any level. And so that was the motivation here. Disadvantages, of course, there's the runaway waypoint formation, eating up memory. The cleanup process can become expensive, and by the cleanup process, I mean when the agent loops back on previous paths and being able to recognize and join those. There's a lot of complexity that is created. Recognizing that you're back to old nodes and not making new nodes on top and so on, it's really a challenge. Now, we've seen that the path quality with a path network can certainly be better than a grid lattice, but we've also seen examples where it has problems, such as the weird tracking back that we saw in a previous example. So we might still want to be able to clean up paths, such as with a string pulling algorithm. And the issue here, though, is while we could come up with a way to do the string pulling, we would be testing against world geometry, which it's hard to make any guarantees about how much geometry is going to be in any given level. Now, the problem also with the string pulling is that we can't pre-bake this, or I guess you could if you cache all of the different possible paths, but that would be impractical for large maps to cache all possible paths that could be returned. So this is likely something that does need to be performed fully real time. Another approach you could have is to use a greedy path following. So you're just going to spread the processing out over multiple frames, because the agent's going to be constantly making movement decisions, and those movement decisions could potentially do some of the smoothing for you. And so I can show you just at a high level how this might work. So in this case, we have this greedy steering following the path. So instead of trying to religiously follow exactly the path, the agent's going to always be looking ahead for opportunities to cut corners. So in this case, it's just going to say, okay, can I see that my current target node? If yes, can I see the next one? If yes, can I see the next, and so on until it gets to the last one that it can see. And at that point, the last one that can be seen means that you looked one further and couldn't see, so you have to backtrack to a node. And so at that point, you're going to steer towards the next to last one that was evaluated, which is the last one that you could see. Just go straight at that node. And then each frame, or every so often, maybe each think cycle, you're going to keep trying to look ahead to see if you can cut off the corner again. And so over time, frame to frame, you might actually create sort of a curved path, or your agent will create sort of a curved path that will look a bit like string pulling. Now, the danger here is you can run into trouble. So, for instance, what if there's a pit that you could fall into? You have to watch out for the raycast isn't going to hit the pit, so you got to deal with that. A common way to deal with this actually is to have an invisible volume that is the raycast will hit. Of course, this volume doesn't impact game physics; it only impacts the raycasting. So that's a good strategy for dealing with pits, is just have this invisible geometry. You can do the same thing over like slow moving terrain, like if you have a mud pit that technically the agent can go into, but you just don't want them to. You can do the same sort of thing, so that would facilitate this kind of greedy steering. And you could also subdivide edges rather than only looking at the nodes. Of course, that would be more expensive, but let's go through just a scenario. So here we have the agent sees the first node. So before it even makes this current frame decision, it looks at the first node, looks at the next nodes, it can see it. Third node, it can see it. Now here's a little gotcha. If you're only doing a raycast, you might have this situation where you're going to go bump into the corner. So you might want to do the point distance to line segment sort of test, but you need to be able to efficiently identify the local geometry and not be testing against like huge amounts of geometry in the world. Many game engines will have some way to efficiently, like runtime, identify, again, something like the bin queue strategy I talked about before for identifying neighborhoods, so the spatial organization approach. But in any case, we want to make sure we have a clear corridor. So like this scenario, the agent can easily go to the second node, but the third node is a no-go because of the corner of that triangle. Now there's some problems with using the greedy steering we've already sort of discussed. So it's not a perfect fix for poor or mediocre path network path quality. The raycasting can still miss some things. The raycasting can get expensive. You can have problems, especially on like variable height terrain or different terrain types that would affect movement speed. So maybe the path that you've searched for has already done a good job of evaluating the quality of the path through edge weights. And now you're going way away from those paths that are guaranteed at a certain overall cost. And now you're like walking through the mud pits and so on, or your agent is getting into some kind of trouble. So it's not really a perfect solution. It can work, especially more in simple games where you have a very simple sort of 2D structure. So yeah, the shortcuts your agent takes might not actually be good shortcuts. And in order for them to be good, the agent has to be really good at in real time evaluating the game world. All right, so let's look at some of the benefits of the path network. So discretization of space can be very small. We can get away from the density of the grid. It doesn't require that the agent be at a path node at all times, unlike the grid. So each cell in a grid lattice is directly associated with the path node. That doesn't have to be the case here, which can be of benefit. And therefore, you can allow the agent to switch between local and remote navigation. Works well with continuous movement agents in games such as first-person shooters and RPGs. Also, we can associate with our nodes some useful metadata, some like gameplay-related things such as cover locations or like collectible pickup points and other points of interest. But downsides of the path network is that, well, one, you might have valid agent positions, but you can't see the network. Therefore, the agent's not able to easily get onto the network. And we talked about, like, well, what are different strategies to get the agent to find the path network again so that it can perform remote movement. You can still end up with jagged path shape, maybe not as like the stair step look of the grid lattice, but you still can have some very goofy looking paths and backtracking. Has trouble with dynamic and rolling terrain because the agent has to make all local decisions as soon as they're going off the path. The storage and complexity issues can run away and maybe even approach as bad as the grid lattice if you're trying to get really good coverage of your network. So you keep adding more and more, and then before you know it, you're no longer getting the benefits that you were hoping to get over the grid lattice. And keep in mind, the grid lattice has that sort of implicit graph structure in it that has associated memory for that density. It has the structured nature of the grid doesn't need to store the 2D vector positions for each cell. It's all implicitly generated. Whenever the agent goes off the path network, it can be dangerous. We've seen we have to rely a lot on that, the abilities of the agent during local movement. And it can also put a lot of real-time computational pressure on the agent implementation. So if we could bake a lot of information into our discretization, then that would be less that the agent has to do. So that might be pointing towards the benefits of something that does define area. So maybe if there's something similar to grid lattice, but didn't have that such the density, the structure of the grid. So that's something we'll see with like the nav mesh, for instance. So, but one last thing I wanted to look at to close things out with the path network, a variant of the path network. And this is a path network with variable size corridors. And so far we've considered corridors being just along an edge, the offset by the radius. So you end up with what looks like kind of a rectangle with rounded caps, or kind of a tic-tac-pill shape in 2D. But instead, if we had variable radius, then it would be more like an ice cream cone, sort of, with a rounded tip. And this could, of course, have different sizes of radius for the nodes. And so this would be able to define an area, a useful area to the agent where the agent is smaller than the corridor and therefore could move around within the corridor. And that could allow possibly for some sort of planning while still fully on the path. There's no need to necessarily leave the path at all times to, say, get around a dynamic obstacle. Maybe you can just move to the left or right within the path, maybe collect things and still stay on the path, or so on. It might make string pulling more efficient. And we have this nice, concise definition of these areas. Their convex structure, and it's defined by the two 2D vectors for where the two nodes are. So the node A, like node A and node B, are each 2D vectors. So that's two floats, and then we have two additional floats for each radius, for the starting point and end point. They each have their own radius. And in terms of determining like a point containment, this can be pretty straightforward to do, because with the point distance to line segment calculation, if you look at the details of an implementation for that, we're going to end up with a vector line equation. So we have a t scalar times the direction of the line. And so that scalar is going to be normalized like 0 to 1 from A to B. A would be 0, and then B would be 1. And so that tells you where you are along the line. And then that can just, with a linear interpolation, that can tell us which of the two, where along the scale from the first radius to the second, like how big that radius should be. So very easy to create our tests. This can work with multiple agents because you can size it as large as you can. And then as these variable size agents leverage the path network for path finding, you can just subtract away, provided the overall network, like all nodes are bigger than your biggest agent, you just subtract from each node radius, whatever the agent's radius is, which will give you a smaller radius. that point, you just treat the agent as a point, not as their overall size. And you just think of moving that point around within each of these convex areas, which are fairly efficient to determine. So anyway, it allows us this planning. Some downsides with using it. There's, of course, the actual generation of these. So baking, what's the appropriate, like how big can you make each of these, the radius for each node, or where do you put the nodes, and so on. It's a challenging optimization problem to pull that off. It still doesn't fully represent the navigable space either. It's only as good as where you have nodes placed. And also, it doesn't accurately reflect the inflection points. You might be able to have an inflection point be contained within an area, but it's not necessarily going to be right at the center of these points. So you got to work with that. So that maybe begins to include some features that you might find in NavMesh, but still has some disadvantages. And so, of course, we'll also look at NavMeshes, which might have some even better ability to fully represent the navigable space. Hello. In this lecture, we're going to introduce the concept of navigation meshes, or nav meshes for short. So this is a popular form of discretized space used in video games. And so we're going to look over the features of the nav mesh and compare it to other sorts of discretized spaces we've talked about previously. So first of all, think about the grid lattice and how it has a uniform structure, and it has this implicit mapping to game world coordinates. So each cell of the grid lattice, we don't need to store any information about the game world directly as a part of the cell. The overall grid, which is an array, or matrix, we have where it is placed in the world according to the grid world corner, and we know the cell width, and for any given cell we know the x and the y, and we potentially could also consider the overall dimensions of our array or matrix. But in terms of a mapping function, assuming that the x and y aren't out of bounds, each cell we can just consider in terms of the xy position as far as mapping to the world. So that would be starting from like the grid world corner plus the grid x times the cell width and the grid y times the cell width. And so that'll give you an offset to a particular place in the world. So we can perform quantization and localization. So going back and forth between the two is pretty straightforward to do in terms of mapping functions. And so any individual cell, there's not a lot that we need in terms of storage. It's just a Boolean that we need, and then some fraction of this data, like the x and the y and the the corner and the width and the grid dimensions, perhaps. So that that demand is spread out across all the cells. So very efficient per cell, but we know that a grid lattice can be very dense and have a big impact on memory, and also impact on search performance. But we might consider, instead of having a uniform structure, we could have a non-uniform structure. At that point, most likely we're going to need an explicit mapping to allow for this dynamic discretization that's going to be occurring, meaning that each unit, so the equivalent of a cell in a grid lattice, whatever this unit is it's going to have to store the information that tells us where it is in the game world. So, for instance, using a polygon, we need to know where each of the vertices of the polygon are in world coordinates. So, comparing polygons to cells, the polygon is going to be more expensive to store than the grid lattice. But there is an advantage here in that whereas with the grid lattice, we have this uniform resolution across the world. So even if you have a big open area, you're still going to have to cover the same area with the same number of cells per unit of distance in the X or Y, compared to a very detailed or complicated area. But when we have this non-uniform structure, we can scale the complexity. So a big open area, we can just have a huge polygon. And if it's a more complicated area, we can have more fine details. So the grid lattice might do a better job in really complicated areas, but on average across an entire environment, we can really get a huge payoff by having this ability to adapt. So this is demonstrating, I guess, the one of the motivations for the nav mesh. So instead of a square, we will have arbitrary shapes, so polygons that can maybe have different number of sides, for instance. But maybe we don't want to allow too much freedom, because that would introduce all sorts of complications in terms of an algorithm. So we probably certainly want to exclude complex polygons that have self-intersection and holes and so on. And even concave polygons could be difficult when you start to consider the concavity that might appear and how you might fit together different polygons if we want to cover some space. But a convex polygon has a bunch of features that are nice and are computationally much easier to deal with. So our nav mesh will consist of convex polygons. So some of the reasons why this is desirable is, well, often is part of the discretization and localization steps. We will want to be able to consider whether points are inside of our polygon, and that it can be very efficient. A straightforward implementation, not necessarily the best, but at least a good starting point, is that we can iterate through each edge of the polygon counterclockwise, and then testing if the candidate test point is to the left of the directed edge AB, and just repeat that over and over. So a point that is in the polygon will be to the left of every single edge. And we can also perform efficient segment intersection or raycast intersection tests. And so similarly to the point test, we can iterate through the line segments and then perform a line intersection test and also a point containment if the edge we're testing for is entirely contained within the polygon. You can check out the computational geometry lectures for more details, but hopefully that gives you a good intuition as to why convex polygons are desirable computationally. Now, they also have nice features for representing navigable space. If we're trying to support an agent that is inside of one of these polygons from a 2D perspective, like walking on a surface, for instance, we don't want the agent to have to do a lot of work to move around in that space. And a convex polygon is going to allow for some pretty straightforward I guess rules for what the agent can do. And that's because you can pick a point anywhere on or in the convex polygon, and from that point you can see with a direct line of sight any other point on or in the polygon. So that means the agent, wherever it is within the polygon, can walk in a straight line to anywhere else in the polygon. So that's a really nice feature. You don't want to have to do anything that is like obstacle avoidance or planning within that structure. The whole point of the nav mesh is to support path planning. So we want to build up from something that is very easy for the agent to work with. So that's something else that is good about using convex polygons. Now, some implementations of nav meshes might restrict things to, say, only triangles, which have even simpler sorts of tests. Of course, they're still convex polygons, but some of the computations can be easier, and others may work exclusively with rectangular shapes, or some limit to how many edges can be present. And so there's different pros and cons from selecting a limit for the specific convex geometry. We won't go into that, but at minimum, having a convex polygon is really fundamental to the nav mesh. So next up, we can think a bit about how this compares with a path network. So here is a scene that shows how we might have a path network defined that has different nodes with edges connecting. So that this describes how an agent can work or walk through the environment to get to different locations. And similarly, we can have a nav mesh that does the same thing. And so you can see in both cases, we have a graph structure. In the case of the nav mesh, the nodes are entire convex polygons. The edges are the adjacencies with other polygons. So any common edge between two nav mesh polygons, that defines an edge. And but we also have this further benefit of an identified area that the agent can occupy. So we know that an agent can't really be on a path network. The agent occupies some area. The agent's not like a point. So it can't be perfectly at a node or on the line. It can only be centered on one of those locations. But in the case of the nav mesh, we have the structure to actually analyze area and know that the agent can be in a particular nav mesh, can move around within the nav mesh in many different positions, and still be able to traverse from one nav mesh polygon to the next, performing path planning, and maybe even refining or revising on a small scale the movement along the nav mesh, which can be beneficial for like avoiding obstacles and that sort of thing. So the polygons and their adjacency defines a graph, and in fact, it's typical that you, as part of generating your nav mesh, will also generate something that is essentially a path network that is part of the nav mesh structure. So for instance, you might pick the centroid of each convex nav mesh polygon to define a node, and then of course you also have the edges connecting each of these nodes that you can determine through analyzing your nav mesh adjacency. So that information is useful for supporting the search and also having a specific path that you want the agent to follow that actually involves specific world positions that are easy for like a character or an agent movement strategy, like a steering behavior, to follow a path. So that's the basic concept of a nav mesh. Next up, we will look into the specifics of generating a nav mesh. So in terms of analyzing a world scene and determining where to place polygons, how to figure out which polygons are adjacent, and so on. So next up, we will look at generating a nav mesh. So there are a number of different ways to generate a nav mesh. We're first going to look at a sort of naive, greedy approach, but we'll also briefly discuss other possibilities that you're more likely to encounter in like a production implementation of a nav mesh. So this can include libraries such as Recast or Neogen, those being voxel-based approaches, and this helps especially with analyzing the environment to get to the point where you can create your polygons. So you actually start with a volume, then you move to the triangles. With this greedy algorithm that we're going to look at first, we're going to assume we're only worried about one level, so we don't need the voxel approach. We're just going straight to the polygons. So the goal of the nav mesh generation, the greedy implementation, is we're trying to exhaustively create triangles through the scene, and these triangles have to be valid. And so what we're going to be doing is iterating through all obstacle boundary points of our world. And so we'll assume that this is the world is bounded by some sort of polygon region. Probably this will just be like a rectangular boundary for simplicity. But we'll have all of these different points, vertices in 2D. So we'll, from this set of points, we're just going to, at this part of the algorithm, we're going to ignore what points belong to what. We're just going to add them all to a pool or a list, and we're going to select point A. And then we're going to iterate through, again, all points, not making sure we don't pick A again, but we're going to pick a point B that is not also A. And then we're going to iterate through and pick a point C that is neither A nor B. This defines a candidate triangle. It might not be a very good triangle, but that'll be our starting point. Now, when we pick randomly of these points in the world, we are going to possibly get a triangle that is not counterclockwise or otherwise not valid. So we're going to screen our candidate triangle. We can check to see if it's degenerate in some way. So we could test the triangle for collinearity, or the overall area of the triangle being 0. And so if we encounter that, we'll say, well, we don't want that triangle, so we'll skip over. Now, if it passed that sort of test, then the other concern is if the triangle is counterclockwise. We want to, just for consistency, for the various tests we're going to be doing, many rely on this counterclockwise nature. So we also want to make sure that our triangle, the 3 points, are listed counterclockwise. Otherwise, the ordering doesn't really matter in terms of like if we have a list or an array, which vertex is first. That's not really important, so long as they're counterclockwise. So if the triangle fails, we're just going to skip it, and we're going to iterate through the next possible pairing and try another one, and so on. And so if we find a valid triangle, Then, well, we might want to add that to a growing list of formed triangles, but we can't just immediately do that. We want to make sure that this new candidate triangle that is counterclockwise and that is valid, not all the points in a line with no area. So we want to test to see if it overlaps with any of the obstacles, or if it overlaps with any of the triangles that have been formed so far in like previous iterations. So if neither of those two tests fail, then we can actually add the triangle, and we'll continue this process exhaustively, trying all combinations of triangle vertices A, B, and C until we're complete. So that's at a high level what the algorithm is doing. So let's start looking more specifically at certain details and how we can actually implement this. So the first thing is, rather than test the entire triangle, we're just going to consider each edge, because if you think about it, if a triangle intersects, it might be caused largely by a particular selection of two of the three vertices, there being an edge. That would be the cause of why an intersection occurred. And there's going to be lots of triangles in that same family. So you have a whole list of boundary points. So you pick A and B, and then C could be one of the whole list minus two. If you've already identified that edge AB is the culprit, then that'll allow you to exclude a whole bunch of triangles all in one test. So we're going to switch to an edgewise way of testing if triangles overlap, at least for part of the algorithm. And then further, there's a few little improvements we can make. So if the candidate triangle edge that we're considering, like let's say AB, so we've picked a pairing of these obstacle vertices, and AB just happens to also be an edge in an obstacle, and that'll be pretty common, that you would maybe pick an edge of an existing obstacle. So in that case, we will not bother testing against all the other obstacles, because we already know it's part of an obstacle. And this is assuming we don't have overlapping obstacles. So the assumption here is that we've already cleaned up or guaranteed that obstacles aren't overlapping. So then we can test the edge against the if we get past that test, if the edge is not part of an obstacle polygon edge, then we can test it by performing checking if there's intersections with any of the obstacles in the scene. So we're going to iterate across all of the obstacles. And we also want to use short circuiting. So as soon as there's ever a failure, we want to immediately quit, obviously, not continue testing when it's pointless to do so. We can also improve our iteration process. We as described so far, to iterate across the obstacle points 3 times, that suggests a loop nested 3 times. So what we're basically doing is performing combinatorially in choose k. Our k is fixed at 3, so in choose 3. So we can define our loops in a way that iterates through the in choose 3 possibilities. So the first loop iterating through and stopping when it's 3 back, and then the next nested loop will start at an index after I, because we don't want to repeat ourselves, and stop that 2 back, and then the third loop will iterate through one after K, or sorry, one after J, which is one after I. So this will allow us to generate our n choose K pairing, or I guess triples, without any repeats of the 3. And so there's a little bit of performance gain there. Even if you do this optimize pairing or indexing into our list of boundary points, you're still going to have repeated edges. And so another thing that you can do is you can cache the results by using something like a hash table, maybe say a dictionary. You could look up to see if during a previous iteration you already stored that edge before. And so these repeats will occur not in the first to the second loop like the A and the B vertex, but it's the fact that we have this third loop that you will restart generating B and C, and then also C back to A is another that will potentially have repeats as well. So because you wind your way counterclockwise around the triangle to form the 3 edges. So yeah, the caching is something that optionally could be done to improve the performance. So next up, we have to consider problems that can arise from just blindly performing this greedy algorithm. And so one possibility is what I refer to as adjacency blocking. And this is where you pick a triangle that can never be adjacent if we're assuming that adjacency is only with a common edge with another polygon. So in this figure shown here, I've got a few different obstacles. Of course, the corners of the obstacles are boundary points. So we have this list of boundary points. And let's just say by luck, you end up, or your algorithm ends up selecting the triangle vertices A, D, and F. Well, in that case, this candidate triangle does not intersect with any obstacles, provided that we're saying that triangle edges that just touch on the perimeter of our obstacle polygons, those are not classified as intersections. So only things that penetrate to the interior of our polygons is going to count. So if that's what we're enforcing in terms of our testing, this would be a valid triangle. ADF is valid. And you can see that maybe through other iterations, well, the triangle BEC would also be valid, and that's fine. We continue and form lots of triangles. Now, when it comes time later to use our triangles that we've created through this greedy algorithm, we want to look for adjacencies. Well, there's no shared edge between BEC and ADF. So what that would mean is there's not, since there's not a shared edge, there's not an adjacency, and therefore there is not a path for the agent to move through. If you look at my mouse cursor, moving between these two squares, there's no way, at least in terms of path planning, for the path planning algorithm to be able to return a path that would go through the red dotted line area. And so this wouldn't be an effective data structure for path planning. However, let's say we ended up with triangle ABF, and then later formed like, say, triangle BCF and CDF and BEC. So all of those triangles, the end result is past the tunnel that's made by the two squares, passing between those, we'll see that there is an edge, and it is common between BEF and BCF triangles. And so therefore we can build our graph structure for the path planning. Everything works out nicely. So we want to find a way to enforce this during the greedy building part of our algorithm. So we're going to have to add some extra tests to this algorithm for it to work right. So this additional test is we're going to check that any candidate edge in our candidate triangle, we want to make sure that there are no obstacle vertices or points that lie on that edge. And so that would mean that, so we say we have edge AB and we have candidate point C. You would want to check that first that A, B, and C is not collinear. But if it is collinear, then we'll check to see if it lies between A and B. So if C is between A and B and collinear, the three of them together, that is our between test. And so if that is true, that it's between, it's not a good edge to use because, going back to the previous slide, you would create this exact sort of scenario. So for instance, for candidate edge AD, point B is collinear and between A and D, and point C is collinear and between AD. So that is something that we can screen for and avoid. So we just skip over the edge and that'll resolve that problem. Another issue is related to floating point versus integers, and in the introduction to computational geometry, this is discussed as a concern where just the nature of floating point values and using epsilon for necessarily using epsilon values, because our floating point values aren't precise. Like there's a bit of error that's introduced, so you have to have this approximate equality that we leverage. The epsilon value is like a fudge factor. So you might set up this fudge factor for a particular test like between, but you have other tests you're doing too. So like you're testing for degenerate triangles, you're testing for whether a polygon is counterclockwise. All of those tests have to agree flawlessly in the context of your algorithm. And that is really hard to guarantee with floating point values. You might tune the epsilon to work in some test cases, but there's lots going on. You have different ranges of values that affect your exponent part of the floating point, which then affects the minimum different value of the floats, and so on. Different tests that introduce different degrees of error, these geometry tests that you're performing. And what can happen is that you get a disagreement. Say you make a decision based on the use of the predicate between, and then like your degenerate triangle test. If that gets out of sorts, then you might, for instance, say that AC, and this figure is kind of exaggerated just so you can actually see some detail. But imagine that you have really, say ABC is really close to being collinear. So it's really close to having a situation where B is between A and C. And you also have triangle ABC is really close to being degenerate. And same with, well, I don't have a vertex shown, we'll call it D. ADB is really close to being degenerate. Every single analysis of all of these has to agree perfectly, or what happens is you don't end up with adjacent edges. And that means that you don't have a path in between these three obstacles. If you use the integer mapping discussed in the first computational geometry lecture, this problem is dealt with and you create a much more stable situation for performing these tests, provided that the geometry tests are well designed. Then you can deal with super skinny triangles as you encounter them. And speaking of long, skinny triangles, that is a problem of the greedy algorithm. Even if you can deal with it fine during this generation, the greedy generation process, it might still have negative effects during gameplay. So if we were to, say, come up with a better algorithm, which honestly you would probably want to do for a production game and not just an academic exercise to learn about the process like the homework in the class, you would probably want an algorithm that makes triangles that are closer to equal edge length and not have this long, skinny sort of problem. And you also, in addition to maybe testing things like whether a point is inside a long, skinny triangle during runtime, because that'll have to be floating point, or generally will need to be just for the standard sort of representation and processing that you'll find in a video game. You're also going to get poor path quality depending on where the point of the path is in the triangle, like say the centroid of the triangle. You have these adjacent long skinny triangles. What you can end up with is like a zigzagging back and forth, because with a long skinny triangle, you are creating a scenario where the centroids move a lot. So you end up with lots of zigzags. You could address that with like string pulling, but it would be nice to start with a path that's already from the start fairly reasonable. And there's better algorithms, such as ones based on Delaunay triangulation, and many others that you can consider. Next issue to consider with this greedy algorithm as described so far is that it's very slow. I think it's big O of n to the power 4, where n is your number of obstacle vertices. So the n choose k is certainly a considerable impact on the performance with the 3 nested loops. Then you have all of these tests that need to be performed in the inner loop as well, which involves analyzing all of the vertices. So that is probably the strongest evidence against using the greedy algorithm for creating a nav mesh. Another thing to consider is the testing against obstacles, the candidate edges that we're forming, and we want to test whether those intersect with other obstacles. Well, we already mentioned that we don't want to have edges that just merely touch the perimeter of an obstacle polygon to count as an intersection. The whole point of the nav mesh is to maximize the coverage of the world, so we want it to go right up to where the boundary conditions are. So we're going to be forming edges of our triangle that are right up against, and so that should not count as an intersection. So it's challenging to deal with that, and the fact that we're picking vertices for our candidate triangles that are common to the obstacles themselves. So that creates a situation where we have edges that are going right through like the worst possible place on the polygon, if it does in fact intersect. So it's going to go between 2 adjacent edges, say at one corner, and then come out at another corner. And it's not necessarily that the 2 points are of the same obstacle. it can still happen just by luck from, say, another obstacle, and then it ends up being just perfectly aligned with two corners of an unrelated obstacle, and it just cuts right through at that point. So this makes things tricky. To exclude things that just touch the outside but still test for the interior, that means you have to do really kind of a specialized test for intersection, especially if our obstacles are not convex. We might have concave obstacles, and we'll see that this is actually kind of important later. So, well, one thing is that I already mentioned that the obstacles can't intersect, and so there are geometry operations beyond the scope of this class that can perform, say, a union of multiple obstacles, and so that would allow you to go from, say, two overlapping obstacles down to one. There's another or other features that we might look into that would result in getting concave polygon shapes for our obstacles that we'll touch on later. But basically, this test has to work with concave polygons unless we broke them up with another algorithm that would do a convex decomposition. So a convex decomposition is not being done, at least in this scenario described here. So we need a test that will work against concave polygons, at least that don't have holes or self-intersections. And so it involves finding these candidate edges that do intersect with the obstacle, at least at points. So we've identified it touches a point. Now, in the figure here, we show one where it's clearly an intersection, the top one. And then the lower figure with a concave polygon, it's touching two vertices, but it's only touching the obstacle polygon itself. It's not intruding on the interior of that obstacle polygon. So we need a way to be able to test this. So we can identify the neighborhood of these intersections, say the edge where it intersects with point A. The neighborhood would be the edge to the right and to the left of that point, if you're thinking in terms of like a counterclockwise winding. So we can then test the opposite point, say point B, that forms, well, it's a position vector. And so we can compare for a given directed edge, we can check to see if B is to the left of it or to the right of it. And so for convex angles, we can check if the potentially intruding edge, if the opposite endpoint is to the left of both edges. If it is, then it clearly cuts into the interior. And then if it's concave, we can check. It turns out you check to see if it's not to the right of both edges. So if the edge that touches a concave vertex is to the right of both of the edges in that neighborhood, then it is leaving the polygon. A concave polygon could be quite complicated and like curl around itself in all sorts of ways. So it's just that at that particular point it doesn't intrude, but it might intersect again later with the polygon. Of course, we'd have separate tests for the multiple candidate places that this could occur. So this is just sort of a high-level description of how the algorithm works, and you do need this sort of special case test. In the homework, this code is already provided to you, but it just sort of demonstrates how the greedy algorithm approach, while initially it seems very simple, you start to discover more and more problems with the approach. So it's kind of like you keep sticking Band-Aids on it to make it work. And I think that's a pretty good description of it. So that leads to, well, is there a better way? And there definitely are. It's kind of, I would say, beyond the scope of this class to be implementing this ourselves. So there's lots of triangulation techniques out there. If we are to consider a triangulation technique, a particular algorithm, we would want one that can handle complex polygons with holes. And that's because if you think about what we're trying to represent, we have an overall world area, say a big rectangle, and then there's obstacles within it. And those obstacles carve out holes of the boundaries of the world. So we might say initially the boundaries of the world define an interior region that is fully traversable by the agent. But then we put obstacles in, and those carve away the traversable area and replace it with holes that are untraversable. So that would be our starting point, this boundary with a bunch of holes for our obstacles or hallways and walls and buildings and so on. From that, you could perform a Delaunay triangulation. So that's a common approach, but it needs to be what's called constrained or constrained edge Delaunay triangulation. And the constrained edges would be where the holes are. There are other algorithms out there as well that might be considered and have different features. Again, it's kind of getting well beyond what we can fit into this class. But if we're going to the trouble to select something new, we probably also want something that's not going to give us a bunch of long and skinny triangles. So that is also a consideration. Delaunay does tend to give triangles that are closer to like equilateral triangles. And the performance can be a lot better than what we've seen with Greedy. Can be as good as big O n log n, where n is the number of our the vertices. And also there are libraries out there. One popular one is Poly2Try. I've got a link listed here. This works well with Clipper, which happens to be the library that's already used in the Game AI homework for the nav mesh. Clipper is used to perform the union of the obstacles, so we don't have to worry about overlapping obstacles, and geometry expansion, which is a topic later in this discussion. Next up, I want to mention Recast. So this is a library that is very popular for creating nav meshes in video games. It involves creating a voxel rasterization of the world. So you've got all these voxels, and within each voxel, the geometry that can be quite complicated in a video game. You can think of like triangle meshes and so on that that would affect the ability for an agent to move around, what surfaces to stand on. So this analysis can be performed in each of the voxels to determine whether the agent would even fit there. And this can happen at multiple layers. So you actually, the algorithm expands across all of the geometry provided from the game world. And then it makes determinations on just little tiny cells of surface. Then it looks to neighboring cells to see if they can safely be stitched together. So you might have slopes or ramps and so on. And so the surfaces can be identified. And so the surfaces are then extracted. And this creates like layers of polygons, which can be triangulated, and we can create the nav mesh. But they're layers that might kind of wrap around or fold on each other in a 2.5 dimension sort of way. So you can think of, for instance, having an agent that goes, say, on a catwalk or a bridge over another traversable area, or you could have platforms that the agent could jump between. So this works really well for gameplay. This is still a pre-processing, typically, process that's performed. You bake the game level to generate the nav mesh. So it's allowing, basically the voxels are a starting point that allow us to better identify navigable surfaces, especially with when multiple levels occur. You still have to perform the triangulation. It's just like an extra step before the triangulation part is performed, and so that ends up being critical for a lot of video games. Now, after you have your triangles, there's still more to do. You need to determine the adjacency of all these triangles you formed. So certainly you can go through your triangles exhaustively and then look at all the other triangles and see if you can find the adjacent edge. That is pretty expensive. You can speed this up quite a bit with a hash table where you hash your edges. So this is kind of an interesting little software engineering problem here, how to pull this off with effective data structures. So you want to, for each triangle, store the edges, and then you see if you can quickly look up the other triangles. But the occurrence of an edge in a given triangle, let's say it happens to be adjacent. Say triangle ABC has edge AB adjacent to another triangle. Well, it's not going to be AB because of the counterclockwise winding. It's going to be BAD, for instance. And so then how are you going to hash this as a data structure? And so we need something that's order invariant. It doesn't matter if it's AB or BA. And well, the dot product, based on the commutative property, it doesn't matter if it's A dot B or B dot A. And we can take the dot product of these position vectors. It's a vector from the origin. It doesn't need to be like a relative position vector. We can still perform the dot product on it. And so that is the base for the hash code. And this allows us to store triangles hashed by common edges and then find these pairings. And so this is a way that we can quickly identify adjacencies for the purpose of forming our it's basically a path network, but the graph structure that we need for our game. Well, it's not a path network until we've assigned a position, I guess, to the nodes. So yeah, graph. Now, another thing that can be performed optionally is triangle merging. That's because there may be larger polygons that could be part of our nav mesh we could have larger than a triangle. So, for instance, we might be able to put two triangles together, go from two three-sided polygons to one four-sided polygon. And it could still be convex, which is our main requirement. And it can still be adjacent to a mixture of other triangles and maybe other four-sided. And we can keep expanding. We can keep merging and merging and merging exhaustively until, like a greedy algorithm, until we have figured out how deep we can go. And that's not necessarily optimal. It's just we've run out, based on the initial decisions we make, we run out of triangles we can merge. But the key here is that we need to avoid merging polygons that end up resulting in concave polygons. And that's possible. You can imagine with a triangle, you could merge two. And if they're long, skinny triangles that are angled just the right way, it would not create a convex polygon. So we can leverage our same sort of hash table of adjacency information we had before to and then iterate on the keys and figure out what pairings we want to attempt So we can do our candidate merge, which is a fairly straightforward operation. Just some basically list operations. We have a list of vertices, and so we have to treat them circularly, figure out where the common edge is, and then stitch together the two lists into a new vertex list to define the polygon. So if it is convex, of course, we continue with it. But now we need to update our hash table structure, and so replace the two polygons with one, but also all of the other adjacencies that those original two polygons had need to all be updated to now have a new neighbor. And so that is straightforward, but I would say error prone. You have to be careful about properly updating the structure. So yeah, you just you continue that process until you've got all of the triangles merged. Next up, you have all of this adjacency information, possibly merge triangles, so you have this more concise representation. Of course, by the way, that helps with our search performance. We have fewer nodes and edges to worry about, so our A* search will work better. So next up, we need to determine, well, where, based on we know that each polygon is a node, but in terms of path representation, we actually need a position. We have to decide where's our position. You might think, oh, I'll just use the centroid, and that will be where it is. But there's perhaps more to consider. But so we need that position for defining an actual path, and then we also need the position because we need to support heuristic estimates for like A*. We need like starting points as the algorithm advances to say, all right, well, what's the distance to the goal to steer where the A* is going. So we definitely need to make that determination of where are these nodes, a specific point position for each. So that is what we are going to look at next. So next up, we're going to look at NavMesh path node placement. So we've already gotten as far as generating our NavMesh in terms of creating triangles. We have perhaps performed merging of the triangles, and based on adjacency information, we have identified the graph structure, but we do need to have a position for the purpose of defining a specific path the agent follows, and also to support our heuristic for A* search. So probably the obvious first approach that we might choose is to put a waypoint in the center of each NavMesh poly. So if you're to do this, you generally will get pretty straight paths, though it will tend to favor going a little bit out of the way, not cutting off corners very effectively. It has also a nice feature that if you're not doing anything to make sure that agents are not getting too close to obstacles, they'll tend to walk in the middle of the NavMesh polygons, staying away from walls so they don't bump into anything. But you can see there's one sort of problem here that is shown with the red line, the dark red line. You can see that if the agent is told to go, say, from one node to the next with a line of sight, well, you're actually going to hit an obstacle there. So So that is a problem, a concern with using waypoints, and that can be worst case when you have long, skinny obstacles, and that's sort of actually the situation we have there. They're not long, skinny triangles, but more long, skinny trapezoids. Um, so yeah, an issue to consider. We might also choose to put waypoints at the center of adjacent edges, or what we might call portal edges, these common edges between two adjacent nav mesh polygons. In this case, the path quality is not too much different than what we saw previously. There's still a bit of going the wrong way, or a little bit the wrong angle initially, and then sort of then heading in the correct direction. But our agent's not turning at the inflection points with this approach. And again, this is without any path refinement, no string pulling is occurring. But the other thing to notice about this approach is, whereas before, when we had any nav mesh poly only had a single node introduced, but now if we have these polygons that are at path intersections, you'll notice that rather than one point, we might have several, as many edges that are portal edges. You're going to have these nodes. Now, the nodes since they're placed on the edge, that means they're associated actually with two of the nav mesh polygons each. But we still end up with an overall increase in the number of path nodes or waypoints with that strategy. If we put our waypoints at the corners of obstacles, you'll notice that in some parts of the path are pretty silly looking, but others can be close to the natural inflection points around the obstacles. Now, this could actually be a problem as well if the agent is bigger than a point, or our nav mesh is right up against the obstacles. Then our agent might get so close to the obstacle, or would if it's trying to follow the path exactly, that they would just bump into to the obstacles. So if you were to do this, you would really need your nav mesh offset from the things that physically the agent could bump into. But there are some nice characteristics here, even though it's a bit silly, like initially in the path, it's getting close to those inflection points. And so that brings us to the next consideration, that we might combine waypoints at both the midpoints of the portal edges and also at corners. And so in this case, we get something that where the agent does tend to turn right at inflection points, and also generally has a pretty good path. And just revisiting the problem that was described previously with using the centroids of the polygons, where you may not have a line of sight from one node to the next across the edge, if the edge is a straight line. And so if you really want to ensure that the agent can always take this straight line path, you want to put these points on the perimeter of the polygon, or at least at somewhere along portal edges for each adjacency. So corners or midpoints of edges will ensure that your agent can always take that line of sight path. So that's like shown on the left figure. The downside of doing this, though, is that you increase the number of nodes and edges that is represented by your nav mesh. So next up, we're going to look at expanded geometry. So with the nav mesh, you would generally have your polygons of the nav mesh right up against obstacles. And so this can create problems in terms of the agent moving around within the nav mesh. They might actually bump into an obstacle. But if we could somehow shrink the nav mesh, or rather expand the obstacles, then we can then end up with a nav mesh where the agent can safely move to any point within the mesh and not bump into anything. So the basic idea is that we look at our agent and consider the radius of the agent. In many cases, you would represent an agent with a collider shape that is a circle in 2D, or in 3D would probably be a cylinder or a capsule collider. Looks like a tic-tac, and stays vertically oriented. So if you project that down onto 2D, which is generally how we think about movement for AI, as treating it as a 2D problem. So in all those cases, we have a circle that we're considering moving around. So we can use that radius as our offset when the geometry is expanded. So if this is expanded before you create your nav mesh, you're then working with your obstacle boundary and obstacle vertices, or the points of the shapes, will already include that offset. So otherwise, you're building the nav mesh just as you normally do. You're just adding this extra step of performing the expanded geometry. And this can be accomplished with other discretized space representations. So for instance, the pictures at the top of the slide show using expanded geometry with a grid lattice. And that just means that more of the cells of the grid would be marked as being untraversable. In terms of performing the expansion, there are different ways you can pull it off. So I've got a figure here that's shown. This is from the Clipper library. This library is actually used in the NavMesh game AI programming assignment. And so that library performs the union of obstacles. It clips them to the boundaries of the world, and it also performs this geometry expansion. So this is all already done for you with this library. So you don't have to implement this yourself in the class, but it's worth considering the challenges of creating expanded geometry. So the big issue with expanded geometry is really the corners. So you might think that it wouldn't be as difficult as it is, or it wouldn't have serious implications to just take an obstacle and then move all the vertices out away from the object. It just conceptually maybe would seem simple at first glance. But let's think about ways that this could be performed. So one is we might expand the edges. So we're exploding the object apart and pushing the edges all outwards. And so in terms of steps, well, each of the edges of our polygon have a normal that we can calculate, and that would allow us to set a direction to move the edge out. And of course, once you move all the edges outwards, we're going to move them by the radius of the agent, and but that's going to leave us with these disconnected edges. So then what we could do is we could grow out all of those edges and then grow them out to the point that they intersect with their neighbor edges. So you could actually we could just find the infinite line that goes through the line segments of each edge, and then find those intersection points, and those would be the new vertices of the expanded edges. So if we performed that operation, now that's straightforward with convex objects. It would get a lot more complicated with concave objects, because as you're expanding in a concavity part of the polygon, you might actually have one edge expand into the other, such that you maybe even just totally erase the concavity and it would become a convex object. It expands so far that details disappear. So in that case, the algorithm would get a bit more complicated, but certainly something that could be handled. But what I want you to consider is the figure at the top here. So we've expanded all the edges, that pushed them away by the offset and grown the edges until we find these new vertices. So it looks okay on the left side of this long skinny triangle, and we can see that our agent depicted in green, that we're generally at least along the edges, we're exactly what we want. In terms of the offset, the agent can go, the center point of the agent can go right up to the edge of the red and just be grazing or just off of the actual obstacle geometry. So this would suggest it would work well. But look at the corners. So the corner on the left is if you put the center point of the agent right on one of the two corners on the left, and one is shown in the figure, we see that there's this little bit of space there. It's not too bad, but clearly there's some error, and that wouldn't be so bad if that's the furthest you ever have to deal with. But notice as we have the much sharper angle, the point of the triangle to the right, when we've performed that edge expansion and then found the new point that connects those two edges, well, now we are well past the radius away from that point. And so if we place the agent center point right on the tip of that triangle, it's nowhere close. And so if we expanded like this, it could create some real problems in our nav mesh, and maybe even cut off connectivity in the nav mesh. So that's a problem. Another approach we could take is to say, well, instead of expanding edges, we could expand vertices. And so in this process, while we find each of the vertices, well, we need a direction for it to go. So we could just look at the two neighboring edges that connect at that point. And so we've got a normal for one edge and a normal for the other. So we could take the average normal, and so that's going to point at like bisecting outward direction of that angle, starting at that point. And so that would be the direction that we move our vertex. Of course, we still know where all our edges are connected. And again, we would have potential cleanup to do for concave polygons, but it is a straightforward process that we could perform to follow this sort of implementation. And well, that'll work fine at the corners, as we can see shown in the figure. The agents, if it's placed at the corner, it is just clear of the corners of the obstacle. But then look at the offset from the edges. So now the offset's not nearly enough. So neither of these two naive strategies are sufficient. So what really you have in terms of the situation, at least for convex polygons, is if you expand, blow up and expand the edges, not increasing the length of them, but just move them all outwards, and you still remember which edges should be connected, well, then you have a radius to that connects. So it's a curvature. It's not a point. And this is this means that you no longer have a polygon. So we have to come up with some, assuming that we do want polygons, and that is a reasonable thing to want in a video game in terms of like the graphics hardware and the computational cost of determining like point containment or intersections and so on. We don't want to be dealing with any curved lines in terms of representing the geometry. So instead, we need to convert it to some kind of polygonal representation. So we're going to introduce some error. It's not going to be perfect. So we're kind of accepting that it's a compromise. So there's different strategies that you could use. You could do a squaring off of the end, or mitering. And this basically it is making some determination of when and how much to cut off. So one thing you could say is within a certain error, we're not going to perform any manipulation of the corner. So we expand the edges and grow them out as in the first example. And we'll just say, we'll measure from the original obstacle point to the new expanded point. And we'll say, oh, if it's within 1.5 times the length of our expansion radius, we'll leave it as is. But if it's any further, then we will cut it off. And so that's the sort of feature that's built into the Klipper library. I forget the exact details right off the top of my head, the difference between the squaring and mitering, but I think one is selective. And then there's also selective, meaning there's a condition, so like the 1.5 distance. But then there's also this rounding option. So knowing that the radius curve is really the correct way to reflect that equal distance expansion of the geometry around the neighborhood of the point, you can tessellate that radius curve at the point. And so that's what the rounding does. And so you can tell through some configuration of Klipper how many segments should be part of the tessellation, and whether it's based on some like dimensions in the space. So maybe if it will say that if any line segment is longer than a certain length, then it would subdivide further. That sort of thing. So again, this is all a compromise, and you can get reasonable, workable results. Now, there are some implications with nav meshes. When you expand in, say, use JT Round, that's a more precise sort of definition for the boundaries that the agent can go. But you're introducing a bunch of vertices that you're going to be using for your triangulation. And that can especially have a big impact on like the naive greedy algorithm with its poor performance of triangulation. But even if you have a better algorithm, you're creating probably lots of tiny triangles around something, a radius that's been tessellated with like a really fine resolution. So you really want to find the right balance, like what's appropriate, how many points. It's probably going to vary based on the exact geometry and the radius of the curve and what impact it would have overall. So these are parameters that you would need to tune appropriately for your game. So expanded geometry is very well suited to improving nav meshes, but it also works with other discretized spaces, even path networks. You could use this for, and interesting, in that case, you would not need to do the point distance from line. And that's because as soon as you expand the geometry, your definition for the agent changes. You're no longer thinking of the agent as being like a circle point with this radius distance that it needs to be separate from everything. You now think of the agent as being a single point. And so this, for runtime performance, this is great. So you've moved a lot of the computation to pre-processing this bake that occurs before the game even runs. You've generated this information that allows you to change the definition of the problem into a simpler problem. And now at runtime in your game, you don't ever have to worry about the agent's distance from the obstacle boundaries or the nav mesh boundaries. You just think of it as a point. And so, of course, there's great performance benefits there when you're trying to maintain a high frame rate. And in terms of planning where the agent can move on the nav mesh, what places it can occupy, well, the agent can be anywhere within the boundaries of each convex nav mesh polygon. And if you want to know where the agent can go, maybe across multiple polygons, you can cast array within the nav mesh data structure. You just cast array. The array doesn't count as intersecting across portal edges. But if there are barrier edges, those meaning there's not an adjacent nav mesh on the other side, those are the barrier edges. Those would be the only edges that count against the raycast. And that's sufficient. You don't have to worry about whether the agent fits or not, because it's a point. All you need are just if there's a portal edge there, the agent can go. And also, I wanted to mention that the problem of expanded geometry is somewhat similar to the issues discussed about the points of visibility for the path network. So in terms of inflection points, the inflection point isn't truly a single point, it's actually a radius. And that is because of this issue. If you think about like sliding a circular shape, like what's representing our agent, if you try to think about sliding that around a point of an obstacle, it's going to kind of roll along that the point of the obstacle and create a circular path for part of it until it can then take a straight line towards whatever its target is. And so that's the exact same issue that you're facing with the expanded geometry. But yeah, so expanded geometry is very popular to use with nav meshes in particular, because it simplifies the runtime performance of the nav mesh, how the game can leverage for the agent any calculations leveraging this information, treating the agent as a single point, and then being able to move around within each of the nav mesh polygons. All right, next up, we are going to look at quantization of game world points into the nav mesh structure, and also path refinement, or what we've been calling string pulling. So let's consider we have some arbitrary point in the game world, and we want to know where in the nav mesh it is. So we could work with the nav mesh itself to try to find the nav mesh convex poly where that point is. So in terms of assessing whether we found our goal or not, rather than just by name identifying a particular node, we would instead perform a convex point test against the polygon. So whatever the game world point is, say project down onto the 2D plane if it's a 3D game, and that's what we're going to test against the boundary. So we could just exhaustively go through all of the NavMesh polygons and then eventually figure out which of the polygons it is, or perhaps it's not in any of them. Or we could leverage a star search to try to find it more efficiently. So in this case, as we're expanding our search and at the part of the algorithm where we test to see if the current node is the goal, well, we would actually, it would be kind of expensive in that we would have to perform this point containment test. But we can perform our heuristic. We know for each of the nodes of the NavMesh, we say have already selected where the nodes are, whether they're the centroid of the polygon or perhaps the center of edges or corners or whatever the strategy is. And so as we're expanding, the heuristic part of A star, we can say do a Euclidean distance calculation. So the test point, we already have that in game world coordinates, and we know where each of the nodes are in the game world. They have a position as well. So we can perform the Euclidean distance, and that'll guide the search in terms of the heuristic component. And so we can continue to expand the search until hopefully we find it. And so that would allow us to quantize the point into the NavMesh graph. But it might not be on the mesh. And so this is an issue that you're probably likely to face. Often with an agent, you are not going to have the entire game world represented by a NavMesh. There's also some inherent error with creating a NavMesh where often because of simplification of the world geometry and the desire to have a simpler NavMesh for performance, it's not a perfect representation. So you occasionally will have game object or valid game world positions that are not on the NavMesh. So you have to consider that as a possibility. So that would mean you would, in worst case, be right back to searching all the nodes anyway and still possibly not finding it. So possibly a better solution in this case would be to use some sort of other spatial partitioning scheme, such as a bin queue, where various game objects would be placed into something like a grid lattice cell, and then within each cell would be a list of objects, this queue. And then you, in terms of finding things that you want, well, some other object, you can quickly figure out, well, what cell it's in, and then you want to know things in the vicinity. Then you look in the neighborhood, which would be the adjacent bins or cells, to try to find things. So you're quickly screening things based on axis aligned boxes to figure out where objects are. So for instance, you could put the NavMesh polygons would belong to these different bins. And so if you have a game world point, you know what bin it belongs to, and then you also have its neighbors, which would be in the same bin and possibly in the other, depending on if how big these obstacles are and whether you store them redundantly over across the boundaries, or if you just pick one to store, in which case you might have to look in a neighborhood. But that's probably a better strategy. You could also similarly use like a quad tree or octree to organize the NavMesh polygons to quickly find where they are in a particular region. That said, Um, it's probably worth trying to avoid ever having to search or match points with nav mesh polygons. Um, anyway, at least where you don't already know where they're at. So, for instance, if you're building a game and placing objects, you would want to go ahead and either have the nav mesh know where they are, or have the game object know what nav mesh it belongs to, or have some sort of lookup table independent of the two, so that, say, the agent, when it wants to know where to go, says, well, I want to find the health power up, or the collectible, or the key to a door, or whatever it is. They can just quickly identify what it is. So this would be something maybe that is automated during a baking process before the game even begins. You also if you have dynamic objects that are being created, they could be created based on known spawn points, and those spawn points would belong to different nav mesh cells, and that would guarantee that you start off with them in a particular place. If they're dynamic in the sense they move around, you would want to maintain coherence, meaning that as the object's moving, it's constantly evaluating whether it's still in the current nav mesh cell, and if it crosses a boundary, like say a portal edge of a nav mesh polygon into a new nav mesh polygon, well, you would update that information so that it would always be able to be quickly looked up without having to do any sort of searching. So coherence with game objects that the agent is interested in is an important thing to consider, and likely something you would want to implement in your own game. Next up, I want to look at the nature of paths that a nav mesh can generate, and so the quality of the path and how we might be able to refine the path, especially in comparison to a path network. So here I've got a path network shown, overlaid on some height map geometry, and it's got some other complicated architecture and various elements. And so we have our path network, and as you recall, it doesn't fully represent area. You might have a number of path nodes and edges that span a particular area, but there's no definition for like safe areas to travel. And that is opposed to the nav mesh, where we do have entire areas that are defined as being safe to travel for our agent. And if we look at a path we get from a path network, we can get a jagged path, and this can result in strange behavior from the agent if it follows very precisely the path. So you tend to see this like zigzagging movement we've looked at in the path network discussion. And if we wanted to improve this, well, to perform string pulling, think that about how this would be a process that would need to be performed during runtime, unless we're pre-caching common paths. Otherwise, this would be something at runtime. With A star, perhaps we've generated this path and returned it, we're about to return it to the agent. If we're to clean it up, we have to have whatever the string process pulling process is. It has to look at the game world features like obstacles and other things that might get in the way of the string being pulled. So yeah, that's potentially unknown complexity to determine. Or we could have the agent have that greedy steering approach that we've previously discussed, where the agent itself is trying to cut off corners. But again, there's a lot of reliance on the agent to be intelligent to do so effectively. But with a nav mesh, once we have a path, we can refine that path within the limitations of the nav mesh itself, or the constraints of the nav mesh itself. We have known structure in that we have connected convex polygons. We don't have some unknown game world features like terrain height and different surfaces and objects. Like if we've gotten as far as creating the nav mesh, these are areas that have been identified as safe for the agent to be located. So in terms of string pulling, when we're pulling the string conceptually, we're pulling it against the boundaries of the nav mesh, not the boundaries of the world. This is a far simpler structure than whatever complexity you would likely have in your game world. So much more feasible to perform refinement to the path, to the entire path in real time. So during the point that the game is running. So it's much more likely to work. And so one such algorithm is the simple stupid funnel algorithm. And it's really simple and a popular approach. This version is especially well suited to nav meshes where expanded geometry has been utilized. And that is because the end result of the string pulling, of course, will tend to be right up against points of inflection. So right up against obstacles. So if you created your nav mesh with expanded geometry, going right up to the obstacle edges or the barrier edges of the nav mesh is really not the barrier of the world. It's just how close the agent can get to the barriers, assuming that the correct radius was baked into the expanded geometry and therefore the nav mesh. So the way the algorithm works is you start wherever the start point is within a given the nav mesh poly that it's contained within, and you look towards the portal edge that like say a star path search returned. So you know that the path traverses across that portal edge. And so you define, so looking towards that edge, you have a left edge and a right edge based on that the direction of travel. You want the agent to travel across that edge. And so you walk along the edges of the nav mesh that are not part of the path. Those will tend to be barrier edges, but not necessarily. And so you sweep the left side to follow the edge, the edges of follow along the left side that are not the portal edges, and keep going to like each corner of the portal edges with consecutive nav mesh polys. And you do the same thing with the right side. So what you're going to end up seeing will tend to be, as shown in on the slide on the figure on the right, you see when you start with A, well, the left edge is way angled way to the left, and the right edge way to the right. So left is red actually because the perspective of the direction of travel. You would be going down, so from your perspective, the red would be left, and then blue would be the right. And so you say move. Well, it looks like it starts with blue first, which is with the right side. So you move down that edge to the next portal corner, and then you move the red down to the next portal edge corner. You'll notice that it's kind of like a flashlight or funnel, as it's called, that's getting narrower and narrower as you parse out further and further, following the convex polygon edges down to the next portal edge. Eventually what happens is you get the funnel gets so narrow that in order to continue going, the right edge of the the right edge of the funnel crosses over the left edge, or vice versa. When that happens, that means the point you just crossed over, that is the next point. So you might go across several NavMesh polygons in sequence of the path before you finally hit a point of inflection, identified by the funnel edges flipping over to the wrong side. And then you start over with the algorithm again. So you then, from that point, look at the next portal edge, and that defines your left and your right. And then you move along based on those non-portal edges, and you're going to start with the one that does not have two portal edges coming out of it. So it's the free side is the one that moves next, and then you go to the other side, alternating. And you just keep going until you get to the goal, and you will have identified a sequence of points that will be the path that you're going to return. Now, again, this really depends on having expanded geometry, assuming you have an agent that takes up space. Now, when you are using expanded geometry, we're thinking in terms of just a point. That's why this works. You can get the agent right up against these points of inflection. But there might be situations where you don't have expanded geometry. So I'm going to show you a variant used in Horizon Zero Dawn. And the reason why they don't use expanded geometry, they actually generate their NavMesh at runtime. That's because they have this huge procedurally content generated world. They have the robo dinosaurs of vastly different dimensions. So they build out appropriate nav meshes based on the different dinosaurs. Like some just ignore obstacles because they can destroy them, just walk right over and destroy them. Others have to move around things. So they really need custom nav meshes, but they don't do expanded geometry because they want the building of the nav mesh in real time to be as performant as possible. So they use a variant of the funnel algorithm that is very similar, but when these points of inflection are generated, it creates an offset from these points to basically serve as the offset of the point of inflection. So a very similar algorithm that looks familiar. You advance either the left or the right side according to whichever side has a free edge to follow. And when you have the crossover, like shown here, so we advanced the left side twice because that was the free edge side. So it crossed over, that identifies the point of inflection. So now what you do is, rather than just saying that is the point, you then determine a line on which to apply the offset. And so this is calculated, I believe, from the normals of the two. The normal the current path of the agent is the left side. It's not the two sides of the nav mesh. But so we have the edge, the blue edge on the left is determined by where the agent was previously, like in the ongoing progress of the string pulling, and then using the side edge of the nav mesh polygon in consideration. So that determines the bisecting line. So you can take the average of the normals of those two directed edges, and then use the radius of the agent as the offset. And so your point of inflection is now placed at an appropriate offset. And can continue on from there. And so it's really the same algorithm as the stupid simple funnel algorithm, but just this extra offsetting calculation. And so that will get good results if you do not have expanded geometry. So you're hopefully beginning to see that there's a lot you can do with the NavMesh structure. It's not just to create you a path network and then forget about the fact that you have all those NavMesh polygons. Those polygons themselves are very useful for other calculations related to movement, including the string pulling that we just looked at. So next up, we're going to look at some of the benefits of NavMeshes and conclude with a summary. So we've discussed before how an agent following a path network will have to rely a lot on its own intelligence or strategies for dealing with circumstances that might be encountered while following a path. So for instance, an obstacle that gets in the way of the path network, maybe the agent is incrementally following the path with some sort of movement algorithm, and we're also checking for obstacles, casting a ray to make sure the path, near-term path is clear. And if there's an obstacle in the way, that would mean the agent needs to switch to going off path, performing some local movement to get around the crate. And this requires a good understanding of the game world environment by the agent in this situation. So for instance, the agent's like on a bridge, and the area to move might be uncertain. So you go to the right or to the left to try to get around. And if you do go to the left, well, if you go too far, maybe you fall off the bridge. But the same circumstance with the NavMesh is that, well, we have a safe known area to test against. We might be able to identify the intersection of the crate geometry with the path leaves, or the NavMesh polygon leaves a little bit of space to the left. And so we don't have to look at all of the game world in terms of any kind of analysis for like a contingency. We only have to look at the NavMesh and the interaction of the NavMesh with whatever's causing trouble, and see if there is still remains a path. So it's a much more constrained problem, much more likely to be reasonable for real-time performance as well. We can also leverage the area representation of the NavMesh to make adjustments to paths that are followed, maybe supporting different unit types. We can have different offsets. We already saw how we can apply offsets with the stupid simple funnel algorithm with the modification that Horizon Zero Dawn used. And so you could make a NavMesh support multiple radius collider shapes to work with the NavMesh. And so just applying an offset similarly that we saw before. And so that this shows how that visually how that might look, so that we have a red path for the infantry and the blue path for the tank. This can be a useful feature as well. You can also use the NavMesh for analyzing the performance envelope of a vehicle. So say you have a very fast-moving motorcycle. In a straight line, it goes quickly, but the turning radius is very small. So you might search paths with a constraint of the vehicle performance that's imposed, and the analysis of this is facilitated by the fact that our discretization of the space has area associated with it that is fairly accurate representation of the full navigable space. And similarly, if we have animated characters like that run and jump, you'll often have animations that are complicated, especially like combat-related animations, so running and jumping. So the agent can analyze whether there's room to perform an animation. So they say know in advance how far forward the agent would end up moving if they did, say, a running, spinning attack or something like that. That is easy to analyze in the nav mesh. Much more uncertain how to perform that calculation in the game world as is. You have to identify quickly obstacles in the vicinity and perform geometric operations on those obstacles. It'd be nice if you could work with something much simpler that had already been pre-baked into a simplified format, and that's what you get out of a nav mesh is something that a data structure that's workable for real-time performance. You also get the multi-level support. We talked before about more advanced implementations of nav meshes that use the voxels to be able to identify multiple surfaces that are traversable by the agent according to their size. And this is seen, for instance, in Unity. They have a built-in nav mesh. So I've got some screenshots here from Unity. And so nav meshes work great for that purpose. And of course, there's well-established automated methods to generate these multiple level meshes. So in summary, nav meshes are very effective for use as a discretized space representation of the game world and serving the purpose of path planning, but also motion planning, have benefits over grid lattice and path networks that we've previously discussed. They are, however, much more complicated to create the nav meshes as opposed to grid lattice and path networks. So that's a bit of a trade-off there, but it does have a pretty strong payoff. So you get an efficient representation of navigable space. You don't have the wasted size that a grid lattice would introduce. It simplifies agent movement and path refining, such as like a string pulling algorithm, which is certainly easier than path networks if you're considering complicated environments that you would likely have in like a commercial game. And ultimately, NavMesh is a very popular discretization method and used in lots of games, and especially has become popular in the last several years. Hello. In this lecture, we are going to consider the use of quad trees and Voronoi-Dirichlet diagrams to serve the purpose of creating a discretized space to support path planning in a game world. So first of all, I want you to think about the grid lattice and how that was a simple structure that we could use to facilitate path planning, but it had this problem of inefficient space representation because it always had that same resolution in the entire representation of the world, whether you had large expanses of the same surface or traversability, or very complicated details. It's always the same memory allocation. So it'd be nice if we could sort of maintain some of the nice features of the grid lattice, but be able to address this memory concern and also the impact on the path search performance, because more nodes means slower search. So the goal is to try to maintain simple convex spatial structure, but reduce these storage costs. And the strategy we're going to use is we're going to try to use low resolution discretization for large uniform regions, but for environment details that are complex and affect the agent movement, we want to use higher resolution discretization around those areas. And so that general approach is what led to the quad tree, well, more generalized sort of problem space, but the ability to represent details on a spatial level according to just the necessary amount of representation. So you might have, say, a traversable area, like a 2D map that's got different obstacles, and you can divide the world up into regions such that some regions that are all the same type, like traversable or not, would be reflected in the largest or largest possible region, or only as small as needed to represent that. Now, in the case of the quad tree, we still have a structured representation, and the structure is that you start with a big square region, and then as needed for subdividing, you break everything up into equally sized squares, four square regions. And so any sort of analysis of the world or the discretization process goes through this recursive process. So you look to see if within let's say you're performing the discretization, you would look to see within the root level cell, which is as big as the world or as big as a very large tile in the world, that maybe you would load in an entirely new one once you reach the boundary. So this would be like whatever the working the working area or scene of your game is. And so in terms of building the quad tree as a discretized space representation, you would see if there is a difference of like a mixture of traversable and untraversable in the cell. So this might be a test of just seeing, are there any obstacles within the cell? If there are, then you subdivide down to 4, and then you test those 4 children to see if there's any obstacles in it. And if you get to the point where there's only one obstacle and the dimensions of the cell are entirely within the obstacle, then you know that you've got a uniform area. So you don't need to subdivide anymore for an untraversable space. And then for a traversable space, you keep subdividing and recursing down until you just have no obstacles intersecting at all. So those would be the two different determining or terminating conditions to decide not to traverse lower. What you end up with is a quad tree. And so it's an actual tree structure with 4 branches at each level. And the leaves tell you what type of material or traversability is in that cell at the very bottom. And so this, as you can tell, only would represent just a subset of what a full grid would be, which would be similar if this tree was completely filled out. Every branch down to a certain depth would be like a normal grid lattice. But since many of the branches don't traverse all the way down because there's not as much detail in that part of the world that's represented, there is efficiency gains there. And so this, of course, that means fewer nodes and better search performance. There's also, it is a structure that is easy to manipulate. So there are fast edits that can occur. This is a video that demonstrates the use of a quad tree in a real-time strategy game. It's by the developers of Gaia Sky, which is, I believe it's just it's not, I don't think it's a game. I think it is like a planet simulator. So you can fly around the universe and check out different planets. But I guess the developers made this as a demo. It happens to be on YouTube. And if you want to check it out further, I've got the link in the lecture notes. But watch in the video, you'll notice there's these different rectangles that the developers periodically toggling on. So it's like a debug view of the quad tree. And you'll notice that there's some big squares and some smaller ones. And also you'll notice that as the units are moving, say a group of units moves into a large quad tree cell, it subdivides it further to represent where in the cell the various units are. And so that's kind of similar to what we saw with a grid lattice, where agents occupying a cell could be marked untraversable, and that would affect other units that are doing their own path planning or local movement. So these edits are all happening, you can see in real time as the visualization changes. Units are moving in and out of large cells, and the edits are fast enough to maintain this real-time performance. So there's some challenges with working with quad trees. Unfortunately, in order to get this variable resolution, we have to work with more complicated data structures. So the grid lattice was a nice flat structure, easy to iterate across cells, look to the left, right, up or down, or diagonal to figure out what neighbor cells are. In the case of the quad tree, the neighbor cell problem is challenging, especially if the cells are non-sibling. So that would mean that if you're writing an algorithm to figure out neighbor cells efficiently, in some circumstances, you're going to have to navigate the tree structure in order to find the neighboring cell. And so that's either directly working with the tree by working up and down the tree, or having some awareness of how a tree is stored in some other type of storage and then being able to jump to the right positions. And so there are various algorithms that I'm not going to cover, but you can research. If you ever choose to work with a quad tree, you might want to look into this particular problem. If you're whatever algorithm you're working on, this leveraging the quad tree, might need to know the siblings of cells. And so that's something you would want to be as efficient as possible. You can also potentially cache the neighbors. Another problem that arises is because you have the resolution that changes so much across the entire area of the quad tree, you end up with points localized in ways that it creates some weird structure and leads to really poor path quality. And it almost requires that you use post-processing just because the paths in practice end up being not so great. You can also get poor discretization of, say, the geometry of your world. If your game world is say something like buildings or long, skinny hallways, those sorts of structures as opposed to more of a sparse environment where you just say a desert where you occasionally have some obstacles here and there, like a few mountains and so on. You can end up having some like high contrast obstacles what happens is you end up with a lot of subdivisions of the quad tree, and it doesn't seem like it's that efficient with space. Even though the quad tree has this potential, say you have a hallway or a room that lines up in just the right way so that it triggers a lot of subdivision just to represent the walls of the hallway or the room. You can potentially fix this if your game from the ground up embraces the quad tree structure. So in this case, you would actually be building your level geometry would be based on where are the valid subdivision lines of the like the grid lines of the quad tree. Where can those lines be? And so if anytime you have a long straight line, you want it to align with what the quad tree can represent. And so that will minimize unnecessary subdivisions. Next up, I want to show a commercial game that used quad trees. And this is Star Trek Armada. It was a game that came out, I believe it was in 2000. So it's pretty old now. It is a real-time strategy game in outer space, but it's a 2D game. And it has fairly sparse environments. So it's actually well suited to quad tree representation. Of course, you can imagine if you're in outer space, there are large open areas where you're free to move your spaceships around. But there are some things like black holes and nebula that several of the, I guess, what you would call a terrain type in this case, just slow your ship down. So I think you can fly through most nebula, but then there's some obstacles you just cannot get through, like space stations and black holes. But you can see the interaction similar to like Warcraft 2 or Dune and other real-time strategy games. It's just the artwork doesn't look the same. But yeah, so they use a quad tree, and so I'll show you a little bit of that, how they did it. Just a brief discussion. There is a paper you can find. I've got in the lecture notes the title, and I think I've got a link as well. You can find the paper for free online, which you might be interested in reading. But they show in the paper how they worked with the quad tree for performing their path planning. So they describe their algorithm and also have some examples, such as these diagrams here. So they actually, based on the quad tree, and it's built out according to the various terrain types and space stations and spaceships and so on that are in the game level. And rather than during the A-star search, performing the neighbor determination, which would be necessary for finding each of these edges. And that's how you would typically do things in a grid lattice, is you wouldn't actually convert the grid to a graph. You would treat the grid as sort of an implicit graph and then just evaluate relative cell positions as needed while the A-star is performed. But in this case, in Star Trek Armada, the developers chose to pre-build a neighbor graph for the current scene. Like right when the search is going to be performed, they build out this graph and then work on that. And so you can see the what's basically a path graph or path network. So you see nodes, which are placed in the center of each cell, regardless of what the resolution of the cell is. and then the edges connecting each. And then on the right, that is a demonstration of a resulting path where you have starting point A and destination B. So those get quantized to the graph, and so you see the little tails of the path that are necessary in order to get started following the path, and then once you get to the final cell to then go to the goal. So it's a very inefficient looking path going, especially starting point going way out of the way. And so this is a circumstance where we'd want the post-processing or string pulling algorithm to be applied. So just at a high level, they have a solution that involves a combination of A-star path planning. So they actually have a secondary A-star process that identifies candidate nodes for the, I guess, the end points of segments that are the optimal segments. And then they do a visibility test so that they can find where they have straight line paths between a minimum set of path nodes. And so the final result is you get a cleaned up path that turns at inflection points relative to obstacles. And while this particular path is not completely perfect, it's close. So you can see that it does have this slightly out of the way where it goes from A to the second node, and then it's the second to the third node, and the third to the fourth node. You can see that it doesn't look too bad, but it's a little bit short of being the best it could be. And so there are other strategies for how to perform the string pulling, and you can do some research if you're interested and look at other solutions beyond the Star Trek Armada one, which is fairly straightforward. So I think it's kind of a practical one to implement without a lot of effort. But here's another one that I found in paper, and honestly, I haven't looked at all the details of how this one works, but I just wanted to show you another example of what a cleaned up path can look like when a quad tree is used. So yeah, quad trees are certainly something worth considering. I would say, especially for outdoor environments. I think quad trees could work well for supporting path planning. So next up, we're going to look at Voronoi-Dirichlet diagrams. And so these are interesting. They're very popular in computer graphics and AI and other computer science areas, and all sorts of other applications. They've been around for, I believe, hundreds of years, or a couple hundred years at least, and are well studied, and often they're involved in all sorts of algorithms. So these are regions that are closest to points in a set. And so I'm showing a 2D version. There are higher dimensional, like a 3D versions, but we're just going to focus on 2D here. And I'm not going to go super deep into details, but I just want to point out some of the ways in at least high level how they are used. So yeah, the regions, which are these polygons in the figure that I'm showing, they're these different colored polygons, and any point within that color, you'll see a little black dot. And so within that colored region, all of the points of the colored region, the closest of all the black dots is the one that's within that region. So for instance, the top left cell, you see my mouse cursor, that point right there, anywhere in this blue area, the closest point is this black dot, not any of these other points. And if you pick any point along a boundary between two of these polygons, then it is equidistant between the two points that whatever the shared adjacency is, it's equidistance between those two. So these are features that can be leveraged. And so normally when you see a Voronoi-Dirichlet diagram, it is going to just show these single points are what's used for the test for what's closest. But you can also have other sorts of shapes as well, which we'll go into in a bit here. But the single point version works well to support path planning in games, but it generally requires manually placing and tweaking the position and possibly other aspects of the diagrams. So you're building a graph from the Voronoi region, or the boundaries of these regions for the path planning, meaning that the edges, the adjacent edges between these areas, those are going to be the edges in your graph, and then the points where the basically the corners of the polygons, those are going to be your nodes. So if you look at, say, this particular picture here, you see that there's all these different line segments of the polygons. And so you could use that for like a path network, and you could perform path planning that way. So this strategy works well for especially avoiding isolated obstacles. You can just drop a point on top, and as long as the polygon is big enough to contain it, then that will mean that the edges are away from the obstacles, and so your agent can move around. Now, the strategy often is coupled with adding a weighting factor so that you can have some of these points have a bigger area, basically. So it's no longer equidistant. It's the point that balances according to the weighting. So you can control the relative size of the regions in that way. So it's something you can kind of tune. Now, this doesn't work as well if you have like hallways and other complicated, like convex sort of shapes. You have to you might need more than one point per set, meaning that one polygon can have more than one point, so it'd still have the same color in this picture, but all the distance tests would be whatever point is the closest of the set of that color. But that can potentially break any algorithm that you're using that works for, say, like the 1 point. You might need to revise your algorithm that generates this for you would be affected. And you could also possibly, if you have manually placed single points, you might end up with edges that end up going through obstacles in your game world. You could also perform like a pre-processing or baking phase that would then delete certain edges that are invalid because they cross obstacles. So kind of a hybrid between a path network and then using these generator control points of the Voronoi diagrams. Now, another approach is that you can use areas. So we sort of saw that with using more than 1 point belonging to the same color polygon. But you can have areas that you use for distance as well. So this is potentially more useful. Well, it's definitely better for automatic discretization, because what you'll end up with is a line separating, like the line that is furthest from any obstacle, or you end up with a graph, a path graph that where all the edges are as far from an obstacle as they can be. So that can be good for motion planning. So if the problem you're trying to solve is maintaining clearance from obstacles, then or maximizing distance from obstacles, then this could be a good strategy. It could also be used for some problem-solving type issues, such as the piano movers problem. So imagine that there are movers hired to get a piano out of an apartment, and it's really tight with hallways and rooms and so on, other furniture in the way. So how do you twist and turn the piano such that you can fit it through an area, or even determine whether it can be done at all? And so this is the Voronoi diagram is sometimes used for that with offsets from obstacles, like shown here. But it is not good for giving you an optimum path, because the best path tends to actually hug close to obstacles, as close as you can get. So cutting off corners, you're not trying to maximize distance from obstacles. So it's a functional graph in terms of getting to different locations in the game world, but it's not going to give an optimum path. So you're still stuck in the situation of string pulling. So it might be something that's really better if you are dealing with like large vehicles or some kind of problem solving that your agent is dealing with, moving like a large structure. In terms of generating a Voronoi-Dirichlet diagram for the non-point version, well, for the point version as well, but you can use a modified version of this Delaunay triangulation to deal with obstacles of a certain area. And in that case, the modified version is constrained edge Delaunay triangulation. And so in that case, you mark edges, like the edges of the obstacles, as being constrained, and then it'll build the Delaunay triangulation that's generated, which is basically a tessellation of this complex polygon. Well, there is a conversion you can do. It's very easy, very straightforward, to go from a Delaunay triangulation to the Voronoi diagram. And so as soon as you have the Voronoi diagram, you now have defined graph nodes and edges that you can then perform the path planning on. And so just to close things out, the Voronoi-Dirichlet diagrams, they are apparently popular in game AI and in commercial games. I think this is probably more the case of a few years back to use them, and so but especially for the manual placement, I don't know about using like the obstacle version to generate the paths that way. But I've definitely heard about it, the use in robotics a good bit. But these the two techniques that we've talked about with the quad trees and the Voronoi-Dirichlet diagrams, both are interesting, and I think that there are certain like game genres or applications where it's worth considering against the other space discretization techniques that we've talked about.